will do the trick. No, I don't think it did. No, I don't see it. I'm not sure. Yeah, I don't think it did. I'm not sure if my chat post was successful either. I can post it. Let me copy the link and post it. Okay, yeah, that'd be great. I think that you should be able to. I think if you have, you have this RSS 20 super vehicles thing, right? Maybe you can just kind of post it there. Somehow, and then we can just get started.
Is it possible to change the title of the old YouTube video so that we actually write in the title, moved to a different link? Okay. Check the YouTube description, something like that. At the very end of the title, or at the very beginning, indeed. At the very beginning of the title.
Got it. I'll just do that.
And I'm also updating the social media.
Okay, awesome. Thank you. So maybe we'll give it like 2 more minutes, everybody, and then we'll start it just 2 minutes from now. Okay, I edited it. Okay, I think that's,
very good. Yeah.
If that's ready, I'll also check it. If that's ready, I don't know. I suggest we get started. Is that okay with you guys?
I would wait 1 more minute to see if people react to that.
Okay.
So if the number of if the number of attendees actually jumps.
Okay. Makes sense.
Varun, is it possible to update also the link from the workshop webpage?
Yeah, I'll do that.
So I noticed that actually there are two different YouTube links now. One that is streaming Varun and the other one that is streaming Sertac.
Oh no. Yeah, so so I think that the link that we've kind of started, I think that link should work. I think that's streaming the main person. When I look at the account that Varun created called RSS20 Super Vehicles, there's like 3 streams there kind of happening. But I'm just going to kind of, I think, suggest that let's just make sure that this last link is streaming the speaker and we go with. I think the last link just kind of changes. Yeah, so it's basically the last link is just kind of, you know, streaming the speaker.
I see.
I might be. I think we're now all set, and I can see that there's a number of people in the last streaming link. I wonder if we should get started. What do you guys think? Okay, that sounds great.
Okay, yes.
Okay, thanks a lot for the quick, and sorry everybody for the technical difficulties. So maybe you know, we can just introduce the first speaker and take it away. Yeah. So our first speaker is Professor De Kroon from TU Delft. Professor Kroon is working on the intersection of micro-aerial vehicles, computer vision, and bio-inspired algorithms. Some of his work recently includes the Delphi flapping wing micro-aerial vehicle. And most recently, they've been participating in a lot of drone racing competitions. And last year, they won the Alpha Pilot competition. With that, I'd like to give it to Professor Kroon.
Well, thank you very much for the introduction, and also thanks to all the organizers. So Varun, Philip, Sertac, David, thank you for inviting me today. So not to lose too much time, I will try to, immediately share. Well, okay, I can only share my screen apparently. So let's see if this goes well. You see the presentation? Yeah.
Yes. Yes.
So today I will talk to you about a computationally efficient approach to autonomous drone racing. And yeah, when I think of Agile flight, of course, you know, thinking about human drone racers is very interesting. But I must think about just animals, right? So this is a tiny fruit fly. What's going to happen here is that somebody's going to try and spot it from the bottom right. It turns around to the top left. And now you may be thinking like, okay, but this is actually going quite slowly. But if you look right in the top right of the screen, you see that this video has been slowed down 150 times. And you know, this is really, really a very quick maneuver. And part of the reason that they can do this is thanks to their body. And so what you see here is actually a drone that we made a few years ago, with which we were able to mimic these maneuvers of fruit flies. And there the challenge was to basically recreate a platform that would be able to flap the wings independently and generate enough torque and forces in order to mimic such maneuvers. But of course, also the intelligence of such insects is important. If you look at the fruit fly, it's able to fly, avoid obstacles, navigate, find food and shelter, interact socially with other fruit flies, learn. And it does all of this for only 250,000 neurons. So that's, I think, truly impressive. But it's also very promising for our agile, fast racing drones and very fast moving drones, because it may be that we can actually do that with very little computation. Now, some of the work that we've been doing in the lab is to use this insect-inspired AI. So on the left, you see one of our Delphi's that was equipped with a small stereo system, and it's avoiding walls all by itself. We published on this in 2014. On the right, you see a swarm of tiny crazy fly drones that we used as a swarm to autonomously explore unknown environments. You see these drones moving through the environment and even avoiding each other, going back to the base station, all with only a microcontroller, so it's very little processing. Now, why were we interested in autonomous drone racing? Because we think that this kind of intelligence can also be very useful and can be shown beautifully in the context of drone racing. So in 2016, there was a mail by the organizers of the IROS drone race 2016. And it was released in May, this announcement, and the challenge was in October. So only 5 months. And we participated because we thought, it's nice to show our approach, but also because we thought, who is crazy enough to actually compete in this? Because it's only 5 months. And there were actually multiple pretty good teams that were crazy enough. So it was a very nice race. Of course, it was the first one. It was a very complex track and the speeds were actually quite low. Since then, it has been organized multiple times. And between IROS 2016 and 2019, the speeds of the winners roughly went up until 2.5 meters per second. So why do we do these competitions? Well, like I said, we want to show the value of our approach to autonomous flight in practice. These challenges, they focus on this fast autonomous flight, which now is getting, indeed, like Sertak said, we're getting more and more the idea that we can do that. But I think 5 years ago, most autonomous drones were really slow. So it's still beyond state of the art. I think it's great to compete with, but also definitely learn from the best teams in the world. And the nice thing with these academic competitions is that teams publish their methods sooner or later, so we can really learn from each other. And competitions require a higher technological readiness level, which I think is very instructive, because you can make something work in your lab, but then you're completely in control of the conditions, the time in which you fly, and the competition is much tougher than that. And finally, we always do these things with the whole team, and I think working towards one goal is just awesome for everybody involved. Now, last year, it was already mentioned, there was the AI robotic racing competition, the first one. It was organized by Lockheed Martin and the Drone Racing League. It was also called Alpha Pilot. And we participated in this competition with our team, the MAV Lab team. And here is a picture of us. So on the left, you have Federico Paredes-Valles. You have Anoush Hegde sitting on the ground. Nile Shet standing in the gate there. Jelle Westenberger on the full right with the remote. And you have Christophe de Wachter with the laptop. It's my direct colleague. And together we have been leading this effort over the years. And he was in the lead for this competition. And I'm on the ground there, which nicely illustrates my role in this competition. So as said, we actually won this. And this is our winning run. And we see some images from the viewpoint of the drone and externally. And this final run took 12 seconds to finish this track. As you can see, we were super happy winning it, although we were also completely destroyed. I must say it was a very, very tight competition. I don't think that will come as a surprise. So we ranked first, but the second team was really only a few seconds behind us. And I don't think it will surprise anyone that this was the WS1-8 team led by Davide. But also other teams did actually very, very well. Also the KAIST team from Korea that have been participating many years also at IROS, winning some of these competitions. And what made this competition really tough is that the drone was actually provided by the organizers, and we had very little access to these drones. While normally you take your own drone with you to the competition. That made it really tough, and I think all teams did actually a great job. What we were very proud of is that our drone speed went up until 12 meters per second in this track. And if you compare that to the speeds that were attained in the IROS drone races, that is of course very high. So we were very proud of that. Now, when I was invited for this symposium, initially I wanted to explain you all about our approach, and that I really wanted to do. And I'm very sorry, but I have to play the Corona card, unfortunately. So as you all know, with COVID, there have been many measures. And one of the consequences for our team was that we had kids at home. We needed to teach elementary school stuff. So we were not able to actually write down our approach, send it in for publication. So unfortunately today, I cannot tell you all the details of our participation. And so I'm very sorry for that. I hope you're not all switching off YouTube and just leaving the Zoom call, because I am going to tell you something about our approach in general and about some of our recent works. And I think you can extrapolate a little bit and guess the kind of things that we have been doing in the air competition. So let's talk a bit about computationally efficient autonomous drone racing. In the IROS drone races, we always equipped our drones with very light processors. And this was on purpose because we want this insect kind of AI that is very efficient. And it led last year to this drone that you see passing very quickly. I don't know if the videos render nicely, but I hope so. So this was a 72-gram drone. And on top here, you see a camera, which is a Geoffroy Smart Cam, and it only weighs 18 grams. It has 4 CPUs and a GPU, and it allows us to detect these gates, as you can see. And we do so with very efficient algorithms. So here we see one algorithm in action, and it uses active vision. So it's sampling pixels in a smart way in order to process only a few % of the complete image. And this makes this method very, very fast, very efficient, and allows, actually we're using only one of the CPUs on this Geoffroy. It allows it to fly. And in these experiments, we were flying around 2.5 meters per second, which at the time was competitive with the drones that were flying in the IROS drone races. And so here you see it from the top. The gates are roughly 1 meter by 1 meter. So you can imagine that this is really a tiny drone. Yeah, and what we like about this is that it illustrates the kind of intelligence you can create, but perhaps on the long run, it even allows people to have a very cheap drone that can teach them how to do drone racing at their home or something. This is an overview of our approach. So on the top right, we have the Geoffroy Smart Cam, and the black block, that's what's happening on the Geoffroy. It's detecting the gates. After detection, we solve a perspective endpoint problem to get the relative pose from the drone to the gate. Then we pass this to one of our state estimation algorithms called VML. And it combines these pose estimates with respect to one gate with a very coarse map of the environment. Now, typically, we don't like maps. For example, the swarm didn't use any map that you just saw earlier. But in a race, you have to pass through the gates in a certain order. So you really need it, basically. But the gates can be displaced. And then, this position goes to a controller, which was just a PID. And this was running in the Paparazzi open source autopilot that was running on a microcontroller on the ESChine trashcan drone. So what are the key characteristics of our approach? Throughout the IROS drone races and also in this article on the 72-gram autonomous racing drone, that we have extremely efficient active vision for gate detection. We didn't use any visual odometry, partly to save on computation, partly because the kind of odometry we had started to fail at higher speeds. So we were only using a simplified drag model to do odometry. We have a very robust state estimation and filtering to deal with the outliers that we were getting from time to time from the vision process. And we have a very coarse memory efficient map allowing for gate displacement. And so these are all green because this is all good. But of course, it's not a perfect approach to drone racing. And so I must say the vision that we had in this paper still depends on the gate being a specific color, in this case, orange. If you get more complex gates, then you need to come up with something else. And we were using PID-based control, which is far from optimal. Now, in the remainder of my talk, I want to focus a bit on this and on a preliminary study that we have been performing to change this and to get towards more optimal kind of control. Now, may not come as a surprise at this point that we don't only want it to be optimal, we also want it to be efficient. So let's get into it. So here we have a drone on the bottom right, and it needs to go through this orange gate on the top right. And that means that there's still an error in the position, EX, EY. And yeah, until now we're using PID controls. So you use this error and you multiply it, for example, with a P gain, and you take also the time derivative and the integral to use the error gains. Yeah, this is requires some gain tuning, but yeah, it kind of works, but it's far from time optimal. I say time here because yeah, we're racing, so in the end, you definitely want to be as time optimal as possible. And so, yeah, PID is just not really an option in this case. Now, what many people turn to then is model predictive control. And basically, then you use a model of the drone. And the typical implementation of model predictive control is to select a sequence of control inputs that will minimize the cost function. And if your cost function is the time, then it will be time optimal if you're minimizing the end time. And what typically happens is you start with an initial trajectory, for example, one of these gray ones, and it's not good enough, so then you may imagine that yeah, that this is actually problematic because yeah, it's computationally expensive. Now, you can save computation in multiple ways. You can make smart mathematical formulations of drone dynamics, cost functions, using aspects such as differential flatness, or perhaps linearizing certain aspects of your system. In this way, you can sometimes even arrive at algebraic solutions and getting very quick calculations. You can also say we take a limited time horizon. So instead of predicting the full control inputs up until your goal location, you can say I only predict it for a few seconds into the future. But yeah, the first option is typically for yeah, some specific cases and not all cost functions. And the second option always is yeah, suboptimal in the end compared to the full solution. And that is problematic. What I want to talk to you about today is, it is actually model predictive control, but we use a deep neural network to do actually everything. And so we teach a deep net to immediately map the state error to a control input U. And if the network does its job perfectly, then this control input will be exactly equal to what the full horizon nonlinear model predictive control would say that you have to do at that point. And so that is the approach. And yeah, the cool thing is that, of course, if you use your full horizon nonlinear model predictive control, then it takes a lot of computation. But if you train a deep net to mimic this thing, then in the end, the deep net can run very fast on board. So what was our training procedure? We used optimal control method using Hermite-Simpson transcription collocation methods. We used SNOPT as a solver. We made a database of 250,000 trajectories in a hyperdimensional box of starting states and with different distances and velocities. I have to specify here that we were doing only two-dimensional maneuvers, so only forward, backward. We're not doing anything lateral. And the final position was always at 0, 0, 0, 0, 0, 0. So also the endpoint was always in hover in this case. And so in the end, this led to around 14 million example pairs of state errors and control inputs. This is our cost function. It has two parts. So the green part is time optimal. As you can see, you have the final time there. So if you minimize that, then you're time optimal. The second part is basically the squared of the control inputs. So you're minimizing your control effort, and that minimizes the spent energy. And you have this factor eta, which basically allows you to mix between those two. Then we have the deep net. So we have a deep neural network with 3 layers, 100 hidden units. Instead of ReLU, we used soft+ activation functions. And I completely forgot to mention something super important. So if you've been paying really good attention, then you've seen that in the bottom left, it's not only TU Delft, it's also ESA. And so this was a collaboration with the European Space Agency. I hope you're not watching, but anyway, so thank you very much, ESA. They have been developing this work also in other studies on spacecraft. So in one of the articles, plus activation functions resulted in smoother trajectories, which then are easier to execute by the vehicles. Anyway, so in the loss function is simply the Euclidean distance between the outputs of the network and the optimal outputs by the optimal control method. Now, how good does it work? Well, actually very well. What you see here is the trajectory in terms of X and Z, and the two forces of to generate thrust and to generate the moments in this 2D plane, so forward, backward. And you see by the graphs that they're almost equal. And so the GNC net predicts very well the optimal control, having an error of around 1% of the generated forces. Now, then we needed to port it to the real drone. So this is the structure that we used. In red, you see the GNC net. It receives the state error, basically. Normally, this would come from our vision pipeline. And then it generates the desired thrust and the desired moments. And these are actuated by our lower level controllers. So PID controller for the thrust, and INDA, it's a low level control method that was developed in our lab to actuate the moments of the quad. And later today, I saw for the talk afterwards, there's a discussion topic on the reality gap, and the way in which we have been covering this gap also in our work on evolutionary robotics is to make use of abstraction. And we abstract away from the raw sensory inputs by means of the output of the vision pipeline, and here by basically sending these commands that can be covered by the low-level controllers. And so then the solution from the simulated world, let's say, can be immediately executed on the drone. Oh, before I do this, let's go back. So I'm going to show you two videos. We compared this actually with a method that was developed some years ago by David's group, based on also the minimum step work by Vijay Kumar. And and then it's not super fair because that method minimizes snap and then has a component where you can try to minimize the time, but it's not a strictly time optimal. But we found that this was the best method to compare with because it's used also a lot in the drone races. As we see on the left, the diff GNC, that's the other method. On the right, you see our GNC net with 0.2. Now they're asynchronous, so now you can hardly compare anymore. What you could have seen is that it's slightly faster, so we did multiple maneuvers. In our zoo, typically it's between 0.3 and 0.7 seconds faster on, let's say, a 5-meter trajectory, going from hover to hover. So are these differences huge? I think on the long track in the end, the difference could indeed be big, but of course they're not huge differences. But what you also see in athletics, at some point, the differences is not going to be half a minute anymore, right? So you need to get out everything that you can. So we also saw this in simulation. So in the left graph, brighter means that the method we introduced with the eta of 0.2, meaning almost time optimal with 80%, has the advantage over the diff GNC method with almost 60% at some points. Very dark would mean that the diff GNC method is better. But actually in the case of eta 0.2, our method is always either equal or slightly better. And on the right, you can see why this is actually. So on the right, you see the solid line is the diff GNC. It's very smooth. To have this minimum snap, it gives very smooth curves. And if you see the GNC net, if you make this eta smaller, it gets less and less smooth. Because for time optimal, you need to sometimes quickly change your commands. Now, to conclude the talk, and then hopefully we have time for a few questions. It is feasible to use a single deep neural network, both for guidance and control. And so, we don't need a reference trajectory. It just generates what would be the best control inputs. But in the real world, we've only shown it on hover-to-hover trajectories. And so, I mean, it did work in the real world. That's already, I would say, a win. But of course, to really show it in very agile scenarios, we should still go there, and we should still, generalize it more, not only going backward and forward, for example, going to full 6DOF. And I hope that the networks will be able to do that as well. So I thank you very much for your attention, and if you have questions, then I will gladly take them.
I think we have about 2 minutes for questions.
I can start. So Guido, congrats for the great work. So the last work is very interesting. Everything is interesting that you do, but this one is also new to me. I have questions related to the training procedure. So do you use simulation? And then if so, what do you simulate? And then is it supervised? And what type of representations do you feed to the network?
Okay. Yeah, so thank you very much. And of course, it goes the other way around. But so for the training procedure, yeah, so it's supervised learning. And so this is actually imitation learning, basically. And so we have this optimal control method that generates all these trajectories. And then along the trajectory, of course, we take every point, and with these optimal control methods, you have these control points, let's say, part of the training set. And then, yeah, we just make a mapping from this state error to what the control inputs would be. But we don't take raw motor outputs. We take the moment that we want, and we take the thrust, and then use low-level controllers afterwards.
And what do you input to the network? Images, IMUs, what does it take as input?
Yeah, so in this study, we use the OptiTrack actually to get the difference in state with the endpoint. But principle, yeah, we can take the inputs from our vision pipeline, because yeah, as you saw in the previous part, like in the middle part, we have the vision pipeline, of course, to map vision inputs to where we are with respect to it. Yeah.
And so basically you could do the same using onboard perception by having a gate detector that then relates and then you compute the error between what you perceive and the global position of the gate. Is that correct?
That is correct, but yeah, of course you know very well as well that yeah, it can be. This is basically not taking into account both parts of the process, right? So we're not optimizing perception and action together. And so it can be that the maneuver, of course, brings the gate out of sight. And that's not a huge problem, but it does mean that at that point you're relying on odometry and no longer on the perception of the gate. And so that's, in this approach, not taken into account yet.
Okay. Thank you.
I think at this point, we're cutting off and we're going to our next speaker, if that is okay for everyone. So our next speaker is Professor Marilyn Smith from Georgia Tech. Marilyn leads the Vertical Lift Research Center at Georgia Tech and is well known for her work on unsteady aerodynamics. Recently also bringing this field of research into the field of drone racing simulators to close the reality gap in modeling highly agile aerodynamic vehicles. And without further ado, Marilyn, the stage is yours.
Great. Please let me know if you don't see my slides. I'm assuming you can see them.
We can see it. Thank you.
Okay, well, thank you. So yes, I'm not actually in the area of robotics, but hopefully this work that I've been doing for vertical lift will be helpful. I hope so. So let me just dive right into what we've been doing. So in terms of, well, let's see. There we go. In terms of why we're doing this is we're working very strongly in transformative vertical lift. Now this can be full-scale vehicles like many of the ones you see on the right here, manned vehicles, piloted, optionally piloted and autonomous vehicles. The problem is that you see is that these are a number of very large and different configurations. Scaling goes from micro air vehicles all the way up to the very large, if you will, craned vehicles. Now they're not super agile, but we do need to be able to model them. And so what we're trying to do is to develop a physics-based modeling approach for the aerodynamics that can be used for a number of different applications. Now, if you look at the literature before we started looking at this, is that there were some explorations of the unsteady rotor effects and then the quasi-steady thrust. We saw very little assessment of the fuselage aerodynamics and the rotor fuselage interaction. A couple of the different papers that did go into it. So Hoffman looked at the rotor vortex impingement, which of course will change your aerodynamic quantities and require different kinds of thrusts. Then we saw that the folks at the University of South Carolina were actually using quasi-steady wind tunnel fuselage data to help with their moments and forces. And then for very specific configurations that they use quite a bit, there was some system ID. But if you look at the current practice, people were using either point masses or frontal equivalent plate force or drag equations. So the question was asked, and hopefully we've answered it, is how important is including the unsteady fuselage aerodynamics? That was our first question. So our motivation here is that what we want to do is to get the aerodynamics much closer to the actual vehicle response and the prior models to help with the design of control laws and the stability characteristics. We're looking for a reduced order model as a solution. We want to be able to have it in real time or non-real time, because one of the things we want to do is that for the piloted vehicles, we want to be able to improve safety. We need to have physics-based so that we can do a wide range of configurations. And so we need those unsteady aerodynamics forces and moments. Something we've been doing just this past year is we've expanded to include the rotor fuselage interactions so that you can have either, like when you're in straight and level flight, you know, you don't need to have a tightly coupled analysis between your rotor and fuselage, because once you know what your settings are and you assume that you don't have a lot of turbulence in the atmosphere, then of course that's just an open loop simulation. But if you're doing maneuvering, then of course you need to have fully coupled, which will cost a little bit more in terms of what it takes to get these applications. And now we're also looking at electric propulsion effects. We're looking at some things for NASA at the moment. Now, just an overview of our methodology. We have quite a few papers, and I'll give you my contact info at the end if you're interested in finding out and reading more about this, or you want to talk to me one-on-one. But what we have two programs. The first program is called GTAB, or Georgia Tech Aerodynamics of Bluff Bodies. What we have here is, this is the core in black, is our module. And then we can connect it up with the flight controller. So whatever you're using for your particular vehicle, it can be connected to. We have our own, and it's set for a generic autonomous vehicle just for testing purposes. But what we have done is we have taken a physics approach to aerodynamics. So we start with a quasi-steady aerodynamics. So we look and we see what happens, you know, when you change the angle of attack, when you change the yaw angle. And from that, we can develop the whole entire 365 degree sphere of all of the different combinations. Now that's fine, but we've shown in prior applications that, you know, when you're trying to fly very fast and agile, there is a phase lag associated with your control inputs and the response of the vehicle. So what we've done is we've taken unsteady aerodynamics, both the classic aerodynamics such as Theodorson, Wagner, Kusner, and then we've also added corrections such as RT Jones, which allows for some bluff body. Now, because these are bluff bodies, they're not aerodynamically streamed vehicles in a lot of instances, and even at some orientations, they lose their aerodynamic capability. Then we've also added shedding capabilities. So we get that extra unsteady physics associated with this. Now, these all combine together to give us our forces and moments, and this is what we go into the control module and see. So the issue, however, when we looked at this is that some of these still cost a lot. Specifically, if you look at our analysis, you'll see that while we can get full-time simulations in compiled languages, we validated very well with helicopter slung loads. This is actually what it was developed for. It was to improve the slung load capability so that helicopters could fly faster. Now, we did identify the significance of the unsteady effects and the configuration details, but the design barrier was due to the quasi-steady data. That data you had to get from CFD, which will take anywhere from 30,000 to 100,000 computer hours, or you need to go ahead and put your model inside a wind tunnel and do those orientations, the angle of attack and the yaw orientations. Now, just from this particular paper, this is flying an S maneuver, and you can see that there is a difference. So, like I said, most people tend to use the flat plate, the equivalent flat plate drag area to get the forces, and they ignore the moments. And so you can see that the characterization of the altitude in this case is quite different between the flat plate, between using just a center body, so that's just using the center piece right here, and then using the entire UAV. So, you know, your predictions can be quite a bit off. And so when you're trying to design a new vehicle, or you're flying into something new or teaming, for example, that can be a problem because you can actually crash at that point. And so not a good situation. But what we wanted to do was we wanted to look at this barrier due to the quasi-steady data cost. So what we did is we came up with a new code called COMPASS, which is Complex Aerodynamic Shape Simulator. And so here you take the inputs to one of these, either CFD experiments or COMPASS, and that's what you feed into the quasi-steady aerodynamics. Now, what we've done here for the complex shape simulator is we take this body, whatever complex body it is, and here this is a little UAV, and we break it up into different shapes. And so when we take those different shapes, then we have found, and we've published this in, I think, the Journal of, or Experiments for Fluids, and we have found that you can take each of these separate quantities, integrate the pressure distribution on all of them, put them together, do some corrections such as interference effects and shadowing when one component is in the shadow of another and the flow stream is coming from the left to the right. So it actually doesn't see the free stream. And then we can get the forces and moments for the entire body. So this is great because we found that it's 5 orders of magnitude less than the CFD. So for the CFD, if it takes 30,000 to 100,000 hours, then COMPASS, depending on how good you are in using it, how complicated your vehicle is, it takes on the order of 15 minutes to 2 hours to build your model. That's great, but how good is it? Because we're talking about CFD. And when I talk about CFD, I have to say that this is a hybrid RANS LES CFD. So if you know CFD, you know those are not your traditional just turning the crank on the CFD. This is very highly tuned, and it's been validated quite a bit. Now, what we get from these different configurations is, I just wanted to show you some examples. So here's a flat plate for drag on this UAV that we saw before. Here's a side force coefficient. You'll see the CFD is in red, and our COMPASS prediction is in black. Now, these were done a priori. We didn't look at the CFD or anything at all. We just did the integrations, and it came out to what it came out. This is our first iteration of COMPASS. So, you know, it's not perfect. You see we have some oscillations and things here. But you see that if you're using the flat plate approach, the equivalent flat plate drag approach, you can be not only off, but you can be in the wrong direction, so that when you're doing your controls, you may be actually telling yourself to go in the wrong direction. Here's an angle of attack, so same kind of thing. You see that they're actually very close, at least in the first order effects. This was version 1. We're in the process of creating version 2 of Compass. And so far, it seems to be much closer. We're getting rid of some of these points and also some of these oscillations that actually aren't seen in the CFD. How does this do? Well, if we compare with flat plate and unsteady predictions just for the general level flight performance, the biggest one that you see is that when you try to trim your rotors, you're being overly conservative. Sorry, you're not being conservative with your flat plate predictions, and so you are overestimating your range of flight time. This can be a problem, especially if you're trying to do a very specific mission. And then when you do the unsteady, I only show one unsteady here because if I plotted the CFD and the compass, they're essentially right on top of one another. So those differences don't make a great deal of difference because those first order effects are the ones that are important here. Now, what about maneuvering? So we started doing the split S maneuver, which you saw in the prior slide. So we're rolling the vehicle, we invert and do a descending half loop in order to get 180 degrees change in direction. I'm sure you're all very well of these kind of maneuvers. So here is an estimate of what we get with this different applications. So you see again, the red is CFD, it should remain red. The black is compass, and then the blue is the flat plate. So everything in here is run through GTAB. You're just getting the different estimations for the unsteady predictions. So we start here at this location, and you see that again, the CFD and the compass are very close to one another. So when you're talking about the cost for doing many vehicles, then having a tool such as Compass is going to make a big difference when you're trying to understand what's going on. Now, we also, as I said, we've just added, just this year, right before the pandemic began, we got our rotor interaction involved. So I wanted to just highlight a few things here. And you see that there is some difference between running just the fuselage versus including the rotors on there so that you get the rotor fuselage interactions. And the differences here that you see in thrust are happening, this is right about when you're doing and coming out of the inversion and starting to fly out again. So you do see some changes. Whether or not it's important for your application is, of course, up to your application. We also see some differences in the aerodynamic forces and moments. You'll see that the rotor fuselage, you get more of an impact so that, when you're doing the downward expression of it, we call it download in vertical lift. When you look at the downloads, it can make a difference to the overall forces that the vehicle will see. So again, depending on whether you need a first order or some of these higher order effects, it can be important. In level flight, it's equivalently the same. You don't see a big difference, but when you're doing an aggressive maneuver, you can see up to 40% difference in the predicted forces and moments. We look here at another case. Here is obstacle avoidance. The vehicle, it was an autonomous vehicle. It was told that when it encountered the obstacle, it was asked to maintain its speed and altitude and to return to its original condition and as fast as possible. So once again, you see a difference in including these unsteady aerodynamics, and you'll see that once again, Compass and CFD are very close, not identical, but very close in terms of the tracked trajectory. Now, this is important again, if you're doing a military operation with a vehicle that's going very fast, and that you're trying to go in and out of buildings. You know, we saw that you can have vision perception and things, but, you know, I think something like this would help with understanding what's going on in your vehicle. The nice thing about some of the things that we are doing is that we can look at what's happening in different situations where we have very turbulent flow. Again, just very quickly, you'll see these differences. You'll see the differences in the responses and the rates. You don't pick up some of the unsteady responses that you get with the unsteady effects. Again, the rotor thrust and things you'll see with the rotor fuselage. But the proof of the pudding is here. This was integrated into the Drone Racing League's sim just last year. And you see that this flight test, let me run it again. This flight test has the real life path with our simulation that I just described to you. It does not have the rotor fuselage effects in it. Actually, what we found is that with this translation that you see here, it actually occurs in here, and then you see a slight loop difference here. That these effects with the rotor fuselage, we believe that based on our approach, that we should go somewhere closer to the real life path in red. Unfortunately, with COVID, we haven't been able to retest it at this point, but hopefully we can do it. But one of the things, if you follow the DRL and their simulations, the pilots have told us that from before, where we have a lot of floating and things, once they've integrated this into their simulation tool, that it flies very much like the real vehicle. One of their pilots was a Georgia Tech student, and he actually helped us get involved with this and helped us test things out. So it's really awesome. So just a conclusion, we found that you really do need to include the aerodynamics of your body when you're trying to calculate some of these. We've used this for some control law design, and we've evaluated it in level flight maneuvers. With our reduced order prediction model compass, we're able to replace CFD and wind tunnel tests to define the quasi-steady aerodynamics. Because remember, what it is we take the quasi-steady aerodynamics and then we do the corrections for the unsteady aerodynamics rather than trying to do everything as one piece. We can save up to 5 order of magnitudes for that. Now, our current efforts, we're doing some high order corrections. In fact, we're in the middle of a test to look at when you're doing high spin rates. We've seen that in some flight tests that we have available to us, that there are some higher order shedding frequencies that we want to capture. We're in the middle of a test to do that. We just got into the wind tunnel Thursday and immediately broke something, so we'll be doing that next week. In terms of compass, we actually have just before the COVID, we took it completely apart. We're developing new user interfaces, some improved corrections for shadowing. We're adding a bunch more canonical shapes. We have prisms, we have cylinders. We're trying to add spheres and things like spheres and ellipses. That is actually should be done in August, but we're testing it out for some beta versions and providing some information, hopefully to one of the folks here within the next couple of weeks, because I did have a change in personnel as well due to COVID. So here, if you're, the acknowledgements, this was developed by a joint consortium of the Army, Navy, and NASA in the United States. And one of my students was also a Fulbright scholar, so he helped work on this. He did the rotor fuselage interactions. If you have questions or you are interested in interacting with us, these codes are available to people, the source codes as well, unless that changes. But you can contact me at the email here below, and I'm happy to answer any questions. I know I'm not talking to a bunch of aerodynamicists.
Yeah. Hi, Marilyn. This is Ashish Kapoor from Microsoft. I'm just wondering, have you thought about using like machine learning techniques such as deep neural networks to model some of these processes from data? And I'm just wondering, like, what is your thought on using such methodologies, and if they would provide any benefit to the modeling part of it?
I do. Now, remember, when we started developing this, this was for very different applications. First, it was for sling loads. We're trying to actually, with this, and the Army's using it now, to train pilots to fly helicopters with slung load simulators on board, so that they are have better safety, and to be able to certify this. We got involved in design for helicopters and UAVs, so control law design and things like that. I don't think the machine learning is helpful there. However, I do think that a combination of the actual aerodynamics and understanding the environmental impacts. Remember those, you know, we always have two sets of errors. We have the aleatory errors and the epistemic errors. Some we can account for in terms of our physics, others we can't. I think a combination of our approach with the aerodynamics along with the machine learning that helps provide corrections in terms of the environment will be particularly helpful. Also, what happens if, let's say that you lose a rotor in flight? Can you correct for that and do that? I do think some of the fast approaches that we heard in the prior talk from TU Delft are important. But I do think that using them together is important. I'm not one of those people that thinks you can throw the baby with the bathwater and just go with machine learning. I think you really need to have some physics involved as well. It's not just pure math. I think we've found that out for many years. I am an older person, but I'm trying to keep an open mind to some of the newer capabilities. But yes, I do. And in fact, if anyone is interested in working on that with us, please let us know, because I think there's some funding that we can possibly tap into to further develop that. Sorry for the long answer.
Yeah, great. Thank you.
Okay, I think we have to move to the next speaker. Our next speaker is Theo Tomic from Skydio. Theo is a researcher at the DLR and a postdoc at TU Munich, working on drone control and estimation, with recently studying like aerodynamic effects on drones. We all know Skydio has been doing some great work, and he's a software engineer doing planning and controls with them. And let's hear from Theo.
Hi, thanks a lot for a nice introduction. I'll try to present this. It's my first time. There we go. Can you see my slides?
Not yet.
Not yet. I'm sorry. Oh, I see. Oh, I'm sorry. Sorry for the technical difficulty. Probably not right now, right? I'm pretty new. I think I have to rejoin. I'm sorry. Let me rejoin real quick.
Okay.
All right, is it working now?
Yes, it is.
I'm really sorry about this first time. All right, so thank you for the introduction. I'm going to talk a little bit about Skydio and our technology. So this is our launch video for the Skydio 2, which clearly shows what we're trying to solve. Comparing to other drones on the market, we focus on autonomy and online obstacle avoidance and motion planning. So the drone can fly itself, and you can do the activity that you want to do. So you only focus on the doing, and the machine is intelligent enough to do everything safely. So with Skydio 2, we're focusing on filming a person, tracking a subject, and we do it with autonomy. We launched this product last year in Q4. It's a consumer video drone built for autonomous flight. It costs $1,000. Before that, we launched Skydio R1 in 2018. We have the press is really good. People are very impressed by the technology, and yeah, we got a lot of positive reviews. So because this is a workshop on Agile flight, I wanted to highlight the technology uptick in the 1.5 years roughly between the Skydio R1 and the Skydio 2. So in the R1, we had 12 global shutter cameras and an NVIDIA TX1, and we reached the top speed of 12 meters per second, partly due to navigation and partly due to hardware, like propellers and shape and just overall size of the drone. On Skydio 2, we made the whole drone smaller. We only have 6 rolling shutter cameras, more computational power, and we reached a top speed of 60 meters per second. So unfortunately, if this workshop were one day later, I could have shown a lot more interesting things. So we're going to have some interesting announcements tomorrow, but I will show what I can for now. So we have this pretty good consumer drone, but in our view, drones can accomplish a lot in commercial markets. So there's a lot of value to be had, relatively low-hanging fruit in terms of visual navigation and obstacle avoidance. So we see the future as drones as a service that live in docks and are dispatched to a central location. So you don't need an expert pilot, or you don't need a pilot at all. You can digitize scenes with millimeter precision or better. There are a lot of inspections that are dangerous and complex that can be automated with software using a tool such as this flying camera that we have. And we can also provide next level situational awareness in emergency responses. So the dock looks like this. It's a, so this is a launch video from last year. We're still working on this product, working with partners. So basically, you have a docking station that charges the drone, that communicates with the drone, can synchronize data, do some processing on site, and then you just dispatch the drone. It flies its for the length of the battery, and then you can digitize the data, process the data from the drone. This is a landing in the dock in very windy conditions. So the dock has some fiducials, so the drone can localize with respect to the dock, and we can land very precisely even in very harsh conditions. Inspection under a bridge is very interesting. So typically, drones navigate using GPS and magnetometers. So that typically doesn't work under bridges. And using our technology, we can, because it's vision based, we can fly very close to these structures. We can fly inside these structures. So here you can see on the left, the 6 navigation cameras on board the drone and the subject camera, which is 12 megapixel camera. And on the right, you can see the obstacle map that the drone is building while flying under a bridge. So typically these inspections require a lane closure on the bridge. They would require a huge truck and some arm with people hanging on top of it. So doing this with a drone makes everything a lot less dangerous and a lot simpler and faster and cheaper. Another interesting thing that we can do is fly inside of a transmission tower. So this has been done in collaboration with companies that do these types of inspections. So it's not like we found some random tower and flew inside. So we are trying to simplify simplify these types of inspections and make them faster. So there's a lot of value to be had in these types of scenarios, even though this is not necessarily fast flight. You can also do stuff like this. This is a little bit of faster flight. I just found this interesting because there's a lot of thin branches in here. This is an unknown environment previously. It's very dense and we can still fly pretty fast in this type of environment. To achieve this, we have 6 navigation cameras. They're 4K resolution, 200 degrees field of view fisheye lenses. They're all processed on an NVIDIA TX2. This is I don't know if you can see me. This is the PCB that we have inside. It's one of the prototypes. That's the TX2. We have a bunch of microcontrollers that are handling extremely low-level controls like gimbal, motors, flight controls, and we also have an image processor, an ISP for recording video. You can fly using a mobile app, a manual controller, and our own controller, which is a beacon, which also has a good GPS in there. So you can also track not only visually, so if vision fails, you can fall back to GPS and IMU fusion. So it's pretty clear by now that our approach to flight is full autonomy, which means the ability to perform complex tasks without a person in control. So this, we believe, unlocks the full potential of autonomous flight. As a comparison between the Skydio 2 and one competitor drone, you can see how tracking works differently when we rely on motion planning and obstacle avoidance from the bottom up. The software stack looks a little bit like this. On the left side, we have the mapping and state estimation pipeline. So we have visual inertial odometry for state estimation. The images are first, we perform semantic segmentation on the images before getting depth data. We create a 3D map of the environment that then goes into a, goes into a motion planning pipeline where we get obstacle avoidance. We go to vehicle controls, and in the middle we have to estimate the gimbal orientation, where the subjects are in the image, and then we track the subjects, and that they also go into the motion planning pipeline. This is an example tracking video of this. So this is fast and agile flight because this is Abe, our CTO. He's riding mountain bike really fast, so the drone has to keep up. The drone has to track him, frame the shot, avoid obstacles, and just track everything. So on this example, we can see what the cameras see. So this is one top and one bottom camera. I'm not particularly sure what the speed is here, but when the vehicle has to catch up, it will typically reach its top speed of 60 meters per second. When you fuse all 6 navigation cameras into one view, this is a 360 degree field of view of the environment. So the drone basically sees almost everything around it. For 3D mapping, we first rectify the stereo images. So we basically have used the fisheye cameras as stereo pairs. So we rectify these images. We perform stereo matching and filtering. We project these points into 3D space and build a map. So this is still a relatively classical pipeline in that sense, in that we still have a 3D map that we build on board of an unknown environment. So we're trying to be conservative in this sense because we want the drone to be safe in any scenario, in any environment. So we would rather slow down than crash in this sense. This presents a lot of, so visual navigation naturally presents a lot of challenges. So these are images from a lot of different scenarios. We have thin branches, sun glare, dirty lenses, motion blur, reflections, textureless sky, water droplets, and similar effects on the camera images. So in order to deal with this, we try to go beyond classical pipelines for depth estimation. So we actually have a deep stereo pipeline running on board the vehicle in real time. We published a paper a while ago about this, and actually, sorry, yeah, I will go a little bit into that later. This is unfortunately not my area of expertise, but this is one very interesting thing that in order to deal with these types of problems in camera images, we can rely on data augmentation and deep learning to learn how to deal with very difficult situations that would be problematic for classical approaches. So these are examples of how the resulting depth images look like in actual images. On the left, we have very thin branches in a forest, and on the bottom, we can see the depth that we get from the stereo system. We can see that the very complex foliage is detected very well. We can also deal with very thin structures, like these power lines in the middle. This is very important because we do not want to hit a power line. And we can also, our system also works well in untextured environments, like in the office on the right, which is very difficult for classical pipelines. We first flew this in July 2018. It's a very efficient network. The very nice thing about having a lot of flight testers and a lot of flight hours is that we can, if we have a crash during testing, we can go back, replay a collision, and then improve on that, like to see things in the future that we had not seen before from the camera data. This is another example of how it looks like from when flying in a forest. On the left, you can just see the camera image. On the right, you can see the depth estimate projected into that image, which shows that even with this, with a lot of glare and similar, works really well. And in complex foliage, on the left, you can see the subject camera image. On the right, you can see the 3D map that we build online. So we see all these obstacles that are very complex in texture. In confined and textureless areas, this also works really well. On the left, you can see the map, and on the right, you can see the very noisy and very textureless navigation camera image. And coming back to the example of the bike ride, it's on the bottom, you can see the depth projected into the 360 equi-rectangular projection, which just shows that what we can see with this type of navigation system. So expanding a little bit on that, tracking subjects, this is a relatively old video of Jack, who is also in the call. So if you have questions, he can also join in. This is a very young Jack trying to run away from the drone. And you can see that we have the range of the tracked subject, the previous trajectory, and their current velocity estimate, which is a very nice input for a motion planning system. Another thing I want to touch on is that we do have knowledge of the dynamics of the vehicle and the aerodynamics of the vehicle. So online, we are constantly estimating the wind speed. So here in this video, you can see flying next to the ocean on a cliff, the wind vector, which is shown on the right, is relatively constant in the inertial frame. So we use this information for planning and control later, which I'll explain a little bit later. Yes, so for motion planning and control, this is an extremely high level image. I apologize because we can't really show that many details in depth. If you're interested, you shoot us an email and maybe come for an internship or come work for us if you want to know more details. But on a very, very high level, so we use images, IMU, and motor speeds for visual inertial odometry, for wind estimation, for external wrench estimation, and similar. And we use this information in a motion planning and control system that is running at 500 iterations per second. It generates a set of control inputs for the drone, and it considers the dynamics, the aerodynamics, and wind. So it's predicting, given these external conditions, what is the state going to be, and what are the control inputs that I need to achieve that. It also considers input and state limits. Smoothness of the trajectory is very important, especially when flying around people. Distance from the subject, camera framing, position of the subject in the frame. So all of these cinematic considerations, as well as distance from obstacles for obstacle avoidance. And if you have more specific questions, I can answer them after the talk. Because of agile flight, I wanted to extremely briefly touch on timescales in these types of systems from our experience. So this is for the Skydio R1. So this is not updated. It used a very classical planning and control pipeline. So basically, between the motors the motor response is not instantaneous. So it typically on that vehicle took about 50 milliseconds so the motors could be considered a time constant of 50 milliseconds. The attitude was a little slower, and the position response was about 300 milliseconds. So when trying to fly very fast and aggressive, the dynamics response of the motors and propellers also matters quite a bit. So if you want to get the most dynamic side of the vehicle, you also have to consider the motor dynamics. You can't just assume that the desired body rates are going to be achieved instantaneously. So this is in the extreme limit of vehicle performance. That works for a lot of cases, but if you really want to go to the extreme limit, motor dynamics matter, and they matter if the propellers are bigger, because the response is slower. And finally, a little bit of an interim project that we had a couple of years ago. We had multi-drone flights without coordination. Now we have multi-drone flights with coordination where the drones avoid each other. So you can have very, very gimmicky videos from this. And with that, I will thank you with the video of what was a couple of months ago our whole VIO team. Gareth, if you want to help him out with this thing that he's trying to build, come join us and shoot me an email. Thank you.
We have time for maybe a couple of questions. Let me just ask one of the questions that was asked on the live stream. So the question about the 3D representation that you use, and did you consider any alternate to like a voxel approach?
We have considered some other representations, but they're, as far as we know, or as far as I personally know, there aren't any mainstream solutions that are really applicable to the problems that we are solving. So far, this type of, so we're using the voxel representation as a means to filter and process a lot of other data. So the voxel representation is one of the views of our internal representation that is useful for some things. But in terms of flying faster in unknown environments, that there might be better representations. Yeah, so we think, yeah, there's nothing that we have at the moment that is in use other than voxels.
Cool. Are there any other questions?
Yeah. Let's see, can you hear me?
Yep.
So I was wondering, it looks like you have fisheye lenses on your cameras, correct? So given that these you said you're using traditional stereo vision, do you have certain regions of these cameras which do not overlap, and are you just cutting out those regions, or what are you doing with them?
Yeah, so we are actually running a deep stereo pipeline, and of course there are regions that don't overlap, and we basically have to mask them out. But we do still have a good overlap to see everywhere around the drone.
Understand.
That's part of the co-design of hardware and software.
Okay, I think at this point we have to move on. Our next speaker is Ali Akbar Agad Mohammadi. Ali is working at NASA's Jet Propulsion Laboratory on the intersection and interaction of control and estimation algorithms. And he has a variety of application-driven publications ranging from autonomous high-speed flight over DARPA challenges, even to extraterrestrial research. And recently, his team has won the DARPA Subterranean Challenge. And without further ado, the stage is yours.
Thank you. Thank you. Can you guys hear me? Yeah?
Yes.
Awesome. I will share my screen. And can you please confirm if you can see the right screen is the one with the notes, or?
No, that's correct. That's the presentation one. That's one.
Okay, it's the good. It's the right one. Okay. Let me. Okay, perfect. second here. Okay, thank you very much. So yes, my talk's focus is going to be on navigation in unstructured environments. And I will try to kind of discuss some of the topics in the context of a different competition called DARPA Sub-Training Challenge. And some of our team members actually on DARPA Sub-T Challenge are part of Alpha Pilot. So we are closely tracking that competition too. We are very excited about it and constantly trying to see how and if we can use some of the technologies from Alpha Pilot in Sub-T, because that will be a very, a great capability for us. But in this talk specifically, I'll discuss some of the challenges on projecting vehicle speed to the mission speed, and basically discuss some open problems in bringing some of those high-speed technologies into overall Sub-T mission. Here's a picture of a subset of our team, basically who are really main force behind many of the results I'm going to share today. So this workshop is focused on speed, so I thought I would open the talk with some updates on the Parker Solar Probe. This is a vehicle spacecraft that is launched in 2018 targeting Sun, and in 2025 it will become the fastest man-made object ever. It's gonna speed 700,000 kilometers per hour at that point. And it's an exciting mission to follow. And just yesterday, actually, 2 days ago, July 10, it detected a new comet, and it's because of its nature and speed and all that, it's bringing very exciting and new type of science. The second update I would like to give before the main topic of the talk is on Mars Heli. This is another exciting and high-speed vehicle that will be launched in about in just a few, in several weeks. Now it's integrated into the rover's belly, and in this video you will see kind of the deployment mechanism. A shield will come off, and then there will be a small manipulator that will start deploying the drone under the belly of the rover. It will release the drone. Rover will go away because we don't want to jeopardize anything about rover. Rover is the main mission. Drone is just tech demo. But then once they are far enough from each other, the drone will fly and explore the surface of the Mars. These are some tests from the vacuum chamber at JPL that has enough similar density of the atmosphere like on the Mars to just verify and validate the controlled dynamics and feasibility of such flight in such thin atmosphere. The speed of Mars helicopter the top speed is 10 meters per second. And it's the entire mission for Mars Heli right now is just a tech demo, meaning there's not a specific science target associated with it. It's gonna take off and land only 5 times and do short missions. But like our rovers, if it does survive that tech demo, then it will be a perfect platform to do other types of mission. And that's part of the effort to JPL. We are working on R&Ds in a hope that if it survives, then there will be new autonomy loaded on it, and new behaviors will be carried out by this Mars Heli and hopefully the future Mars helicopter missions. On the slower side of the spectrum, we have Mars rovers. And in particular, I would like to highlight the difference between Mars 2020 rover, which at the bottom of the page you will see its max speed, very slow, with a fetch rover. That's a potential future Mars mission, sample return mission in a few years. But what I would like to highlight is fetch rover has about double the speed of, even less than double the speed of Mars 2020. But look at the mission speed at here. So the mission speed is about, or path trajectory following the speed is about 11 times more. So this is just one example to highlight mission progression speed is not always directly, of course, influenced by the vehicle speed. And as the environment gets more and more extreme, there's a higher disconnect here, and mission progression speed is slower. So what do we mean by extreme conditions? This covers a vast or wide range of conditions, including a traverse case where you're dealing with off-road environment, unstructured, muddy terrains, things like that. The challenges can come from perception side, where you don't have GPS, you're dealing with variable illumination conditions, obscurance, smoke, dust, fog, and you're flying in a cluttered, obstacle-laden environment and have very limited field of views. Also, the mission could be extreme from operational or resource perspective, where you have very limited compute, which is typically the case in space exploration. You're very limited in terms of energy, or there are really high risks in terms of the cost of the mission, or you're much more safety critical than normal missions. So with that intro, in part one of the talk, I will focus on the DARPA Subtraining Challenge as a representative and a good example of a mission that includes some of these extreme conditions, and highlight how, you know, the need for overall mission speed. I'll discuss that need and talk a little bit about how the individual vehicle speed can be projected to that. And in part two, as time permits, I will go into a little bit more details about our autonomy framework called Nebula, and discuss some preliminary steps we have taken to handle some of these extreme conditions, and discuss open problems, a lot of open problems in those domains that are still remaining. So what is DARPA Subtraining Challenge? The main objective is to explore autonomously fully unknown environments. And the sponsor, DARPA, has picked underground environments that motivates further autonomy, as you can assume least about the structure. There are 4 competitions in the span of 3 years. Started by the tunnel competition, man-made tunnels, in August 2019. Then we went to municipal urban type of structures in factories, industries, as well as you know, metro subway-like environments. The next phase was supposed to be in natural caves in August of 2020. Due to COVID, now it's being shifted to sometime in fall. And the final event will bring together the mix of these different characteristics of environments in August of 2021. It has several elements of extreme conditions. From perception side, it has all sort of variable lighting, obscurance in the environment, and it's of course GPS denied. It's a challenging environment from comms perspective, communication. As you lose very soon line of sight, there are multi-path environments, and they're, you know, faded and degraded links. Mobility-wise and traversability-wise, it's a pretty stressing environment with all sort of elements, including narrow passages as you know, wide as only 80 centimeter in the course. Operationally, also it has some challenges. Where here is, it connects further to the theme of this workshop, that we need to explore a multi-kilometer long maze only in less than 60 minutes. There is no prior map available, and no human is allowed to enter the course prior or during the competition. We only see where robots were after the entire competition is done. Usually DARPA gives us a quick tour and shows us, okay, here where your robots were exploring. There's one human supervisor, is Alad, who is external to the course and can talk to the vehicles if and only when communication is established, which sometimes is even much harder than the autonomy. So many teams actually went with the just pushing for autonomy rather than trying to establish a comlink. In terms of scoring, DARPA motivates this behavior by distributing objects, 20 objects in the course, such as gas leak point source, cell phone that you can detect with, let's say, Wi-Fi, survivor mannequin, helmet, drill, fire extinguisher, certain objects that are predefined. We know their types, but we don't know where they are and which ones are distributed. And each team has a 1 hour slot that we goes and competes and comes out in a sequential manner. And each team can get 1 point per object if the robots can get to the object, if they can detect it and correctly classify it, if we can say where the object is with a 5 meter error, less than 5 meter error, in the global coordinate frame with respect to the surface reference frame. And somehow within that 1 hour, we need to communicate that back to surface, either by coming back, driving, flying back, or somehow establishing a communication link to say what we have found where. In the first 2 rounds, tunnel and urban circuits, there were 14 teams from more than 50 institutions. There were a lot of different types of technologies, more than 20 UAVs, more than 60 ground robots, and deployed, and one very cool robot, blimp, that you should definitely, if you haven't seen, watch some videos of it. It's very brave idea for this competition. In general, you know, for us being in that environment with all of the teams and expert in robotics have been an amazing, rewarding experience to learn from fellow roboticists there. And our team, similar to many other teams, participated in the competition with a multi-robot solution, hence the name. Collaborative Subterranean Autonomous Robots, CoStar, is the name of our team. It's a collaboration between JPL, Caltech, MIT, KAIST, and Luleå, with several industry partners. And in terms of results, you know, we are still quite far from, you know, solving the challenges in this problem, but the developed solutions so far helped us to win the last round. But I would like to highlight, just to tell you how much this mission speed is important, is that from the 40 points, 2 courses, each course 20 points in the last round, from 40 points, we only got 16 points, which is less than half of the points. That means there's much more need there, and a lot of open problems to explore further parts of the environment and have a faster mission. So in terms of solution and concept of operation, ConOps, our ConOps rely on complementary capabilities from mobility and perception perspective. We try to create a communication and wireless mesh network that basically, by dropping communication nodes like breadcrumbs at the entrance of the course. But very soon, due to the complexity, of course, we have to leave the communication range, and beyond that, robots are autonomous and on their own. I think I intentionally draw some green lines here. How can I erase those? Maybe I can. Okay, I will leave it those for now. And won't touch the mouse. In the first year and the year leading to the first competition, here at the top you see the robots that we worked with. Different types of robots, heterogeneous systems from wheel to track to various types of drones. And in the second year, where we had the more focus on verticality in this space and stairs, we added legged platforms to our robot fleet and increased the autonomy level in the existing robots to explore further and handle more complex and more maze-like environments. So I have a short video here to give you some impressions of the course elements and some of the technologies and solutions we have deployed in the first 2 competitions. So what you see here is called the staging area, where our team prepares the robots, but when the mission starts, these team members cannot talk or touch the robots, and only a human supervisor, if any information coming from robots, will be able to see those data. So here the mission starts, robots pass that orange line. After that, you know, There's no communication with the robot. Here is what our human supervisor, the single human supervisor, will see, the map created by the robots, while there's a communication link closer to the entrance. As robots start exploring the environment, the other robots follow them and try to maintain a communication chain closer to the entrance. As they explore, they create a 3D map of the course and use it for localizing objects. And they do so in a multi-robot fashion, where you see the map jumps are the points that robots come to rendezvous points and try to merge their maps to have a unified representation of the environment. This is a two-story, two-level version of the map where our legged platforms go down and up the stairs. We need to do so in perceptually degraded environments, in dark, fog, smoke, and also traversability-wise, it's a pretty harsh environment. Here is a footage from Arch coal mine in West Virginia, 900 feet underground, where the robots are trying to analyze traversability of the course and pick the best trajectories. And when a part of course is not traversable for one type of robot, the other type, like a tracked vehicle or a legged platform, comes to explore more higher slope area or stairs in the environment and continue the mission in a multi-robot fashion and cover more of this space. In the background, we have this information roadmap. It's a graph that captures the connectivity of the free space, and we populated it with all sorts of information from traversability, localizability, how communicatable each part of the course is, and it will help us to do this kind of coverage, that robots go into narrow passages, search different rooms or different parts of the course to find different artifacts. They do so in a multi-robot fashion. Here's a favorite moment for me in the multi-robot coordination. Two robots at the rendezvous points are talking, exchanging information. The third one, doesn't care, find a very narrow passage in between the two first ones, and then continues its own mission. And when the other two are done with exchanging information, they continue their own mission and explore the rest of the environment. We try to rely on high fidelity simulation environments as much as we can to verify, validate some of these multi-robot behaviors, and then deploy them into the course. This is a little clip from the machine learning aspect, where you see the camera feeds on the left, and on the right, it's the our machine learning module that spits out the anomalies and objects in the environments and try to detect and recognize those. Here you see dropping the communication nodes like breadcrumbs to create a wireless mesh network closer to the entrance of the cave. But as we go further into the cave and underground environment, we lose communication. This is, here you see a robot that we have lost for 20, 30 minutes. And then when it comes back to the communication range, it dumps large amounts of data, and we extract the map and artifacts it has detected. Sometimes there's not enough time for robots to come back to the surface. We are very close to the end of mission, or a robot is stuck. So we try to leverage our data mules or drones try to fly in pre-mapped areas a little bit faster and basically explore the environment. This is footage from another coal mine in Beckley in West Virginia. That drone is flying into in a GPS denied environment, and basically trying to get to these other vehicles, grab the data wirelessly, and come back. To handle the operation time, Rollercopter is an idea we have been working on for some time. That is a system designed mainly to roll on the ground, but it can fly when needed. Here is a little footage of its deployment in one of the DARPA events, where on the right-hand side you see some internals of the algorithm and hazard avoidance, and on the bottom left you see how perceptually degraded the course is and the level of dust in the environment coming out from the airflow of the propellers. So I hope that kind of gives you a little bit bigger picture of what the competition is about and some of the technologies we have been working and the challenges in this effort. So our autonomy solution has been integrated with more than 10 robots. And in terms of numbers on a single robot, we have been able to enable or in the competition setting, during the competitions, we have been able to explore more than a kilometer in 1 hour with a single robot and map about 2 kilometers. And to extend that to larger environments and explore further, we have tried to deploy multiple robots and use more complex ConOps. But so far, we have been able to operate 5 robots simultaneously in the missions. And our goal for the next round is ideally to be able to operate 6 robots simultaneously. So I will, will not go over part 2 in detail, but we'll just, in very high level, discuss a few of open problems in front of us in this challenge, and we'll discuss some kind of our perspective and very preliminary steps and the directions we have, taken some preliminary steps in to address some of these. So in high level, in Nebula, we look at the problem of coverage and exploring the environment in an efficient way from the lens of predictive behavior. So we try to enable the higher levels of coverage. We try to enhance our capabilities to better predict the outcome of behaviors and uncertainty in the environment. This is to control the surprises in the environment and minimize risk so that we can continue on the plan that we have in hand rather than reacting and changing the plan, because we have found that reactions and changing the plan, one of the main reasons that the entire mission progression is slowed down. And to do so, we, compared to traditional autonomy frameworks, that is a collection of modules like localization, mapping, health management, and so on, we try to model interactions between modules and formulate the joint problem. And a concrete good example to clarify on that is, for us as a robotics community, we know that solving the SLAM is quite different. Solving simultaneous localization and planning is quite different from solving localization and mapping separately and putting together the solutions, right? So we are trying to push the same philosophy along the other edges and have simultaneous localization and planning, a SLAP or a SMAP for mapping and planning, as well as other edges. Of course, this is just showing the vision and direction we are going along. Some of these edges are realized with our solution, some are partially realized, but a lot of them are still open problems that we are, we would like to see solutions from community or ourselves, try to develop solutions to deploy in the future, versions of our solution. So I'll skip some of the details here, and we'll just, go highlight a few topics here and conclude the talk. But in terms of the open problems down the road for us, one of the biggest ones, especially the one that is most relevant to the drones, is robust navigation. Just dealing with perceptually degraded environments. When you don't have GPS, you go from dark to full lit. You are dealing with obscurance and self-similar environments. This we have seen not only for our team, also for other teams, is probably the main reasons drones either stopped, were very slow, or crashed in the competition. And that's why we see a huge shift and focus. Actually, most of the scoring robots so far has been ground robots. I would say probably less than, overall across all the teams, maybe less than 5% of the points have been scored with drones. so far, which is something all the teams would like to change, but it is difficult. So our solution for it has been to rely on multiple different sensing modalities to handle these cases, and again, take certain actions that minimizes the uncertainty in their selection and fusion. In the second challenge is having that 5-meter accuracy over 8-kilometer long course. So SLAM is a huge challenge for us, of course. Again, in the interest of time, I will skip these and would be happy to talk more offline. Risk-aware traversability is definitely another huge challenge for us. And we have been leveraging some of the past work on our efforts on fast vehicles, but in this competition, we have been pushing further on adaptation and try to learn more on the dynamics and be able to adapt to these unknowns in the environment to enable actually projection of those vehicle speeds to the mission speed. And finally, the global planning and overall mission planning and multi-robot coordination has been a huge challenge to enable the overall mission speed. And our approach has been through POMDPs and Markov decision processes to take some preliminary steps along this to solve this problem. So with that, I would like to conclude the talk by just highlighting that these extreme conditions introduce a lot of challenges, but also opportunities to impact many different sectors in robotics. And I think as a robotics community in general, these are really interesting problems in front of us. And we, as in the CoStar team, would really like to see solutions from community, and us ourselves are pushing to take further steps along these directions. With that, I would like to thank you, and sorry I'm a couple minutes past my timeline here. Thank you.
Thanks a lot, Ali. I think let's move the questions to the chat, if you don't mind, and we can go to the next speaker. So our next speaker is Dr. Ashish Kapoor from Microsoft. Dr. Kapoor is a research manager in the aerial informatics and robotics group, Microsoft Research, and a lot of us know his recent work with Microsoft AirSim and probably the related works that are in modeling, simulation, and learning-driven approaches to robotics. I'll give it to you. Sorry, I can't hear you yet.
All right, there are multiple mute buttons, so it's confusing. So hello, everyone. Can you guys see my screen?
Yeah.
Okay. All right. All right. Yeah. Thanks for the invitation, and indeed, it's a very exciting program. So I'm happy to be giving you some of the overview of the work that we are doing towards building a drone race worthy simulation. Again, this is a borrowed term from airworthy. If you're a pilot, you know what airworthy means, and this is kind of a borrowed term from there, calling it drone race worthy. This is joint work with many folks across many groups. So on the far left, this is the team from Microsoft. Consists of researchers and research engineers, spending their midnight oil, and some of the things that I'm going to talk about. Team from Stanford with Max Schwiger. So his students and himself, they've been the ones who proposed the idea of organizing some of the drone racing competition and machine learning venues. So very thankful for that. Together with the group from Zurich under Davide. I mean, we've been in contact through phone calls and through various engagements over academic ideas that are coming to fruition. And finally, in the group from CMU under Sebastian Scherer, who's been helping us quite a bit with sim2real work. And again, a lot of work that I'm going to talk about is work in progress. So, and all of this work is pretty much in the open domain. So, we'd love ideas, and if you're interested to work with us, that'll be great as well. So moving on, let's see. So my background has been in machine learning. I'm a machine learning turned roboticist in 2013-14, so relatively new to to the game, given the experience and amazing amount of expertise that this crowd brings. So given a machine learning researcher, I always had issues in going towards field robotics, just because the amount of work, experience, as well as expertise that's needed to build and fly a real world robot is extremely difficult. So consequently, we started looking at the modeling and simulation, which has been the foundation of modern engineering, from your medical processes to chemical processes, weather phenomenon, pilot training, and more recently, machine learning and robotics. Right. So the thing is, all right, how do we convert the hard, difficult field robotics problem into a software problem? And consequently, AirSim was released 3 years ago, which was essentially, trying to solve the problem that we were facing. We were a small team of roboticists in, in Redmond, in Seattle. And, if you've seen the movie Sleepless in Seattle, we have 9 months of rain. And we were having extreme challenges trying to, do any meaningful field robotics at that time. So we kind of built this simulator for us. And it's now an open source project, and I see many of you might be familiar with it, if not using it actively. So this was really built for our research needs, and research needs especially catering towards machine learning. So while there exist a lot of simulators that are trying to address different part of robotic stacks, this was specifically targeted towards solving machine learning problem, and specifically deep reinforcement learning and deep machine learning. And again, this was the first attempt, and nowhere it was as sophisticated as other simulators in terms of the lower levels of the stack, like agile control and things like those. This was very much operating at the planning layer at that time. It's like, all right, I see an image, what can I do based on this image? If I have a low level controller, such as a position hold, or go to a GPS waypoint, or things like those. So this was really targeted towards solving those kinds of perception and planning problem at that point. And of course, over the time, the field of drone racing matured, and this is a very exciting avenue that we want to pursue as well. Again, we are not alone in this quest. So, from Sertash's group, Flight Goggles, if you participated in an Alpha Pilot Challenge, probably you are familiar with that. There have been attempts at trying to create a drone race airworthy simulation. Similarly, corresponding to that, simulations have been, this trend of generating data sets that can help with the problem. So the Blackbird data set is kind of, I see as a parallel to the Flight Goggle work. Similarly, from Davide's group, there have been a lot of pretty interesting data sets that are looking at the challenge of drone racing itself. And of course, there are many competitions out there, at least 3 competitions that I'm aware of. The very first being the IROS competition, the series of IROS competitions that has definitely helped push the state of the art. And it's amazing to see the progress that has been made over the years. The more recently concluded Alpha Pilot Challenge. And finally, we organized, what we call Game of Drones Challenge at NeurIPS. Again, with the focus of harnessing, enabling, and attracting folks from machine learning and AI community who bring a lot of in-depth experience in machine learning, reinforcement learning, semi-supervised, self-supervised, all kinds of flavors, but are not roboticists from training. How do we enable them to come and work with us in this exciting field? Right. So when we think about autonomous drone racing, again, to me, it's one of the ultimate AI complete challenges. It brings together, the tasks of complex perception, planning, and control at high speeds, using fairly difficult maneuvers that are not just based purely on the dynamics of the system, but also the physical properties. So, for instance, many of the human drone operators might use maneuvers that just lets the drone tumble in the gravity, and then they pick it up and they'll just go and fly. It's not just the pure system dynamics as in how we control drones, but how the gravity operates on the drone as well. There are interesting game theoretic challenges. So when you are competing against another person or a group of competitors, you also need to model the human element to it. There's a strategy there. You can try to model how the other competitor is going to, for instance, fly their drones as well. So there are very interesting dimensions that are brought in this problem space. And if you look at the spectrum of the research, it's really trying to push performance, and that's great. But two particular questions that I'm specifically interested in answering with the line of the work that I'm talking about is, can we enable application of recent ML and AI advances, such as reinforcement learning, self-supervision, unable to harness clouds, etc., in order to solve these problems? And more importantly, how can we bring along the members of ML and AI community who are not roboticists yet, but might have insights and ideas which might actually help us accelerate progress in this space? So to that end, there are three high-level components that I want to touch upon. So first thing is just the drone racing fabric itself. This simulator by itself is not useful unless we reveal constructs that allows researchers and engineers to create scenarios to enable them to to evaluate and measure concretely the progress they are making in the field. So that's the drone racing fabric. That's very important. It's the SACART that it's the scaffolding that permeates through your simulation world. The second thing that I'm going to talk about is basically stemming from the fact that modeling physics in simulation is one of the most challenging tasks that we have come across, not just because of the system dynamics, but also the variability of each robot. Each robot is unique. Sure, they might be manufactured through the same pipeline, but the moment it crashes, the moment it hits the floor, the moment it lands hard, there are interesting changes that happens in the body itself. Consequently, we've been thinking about scalable ways to model physics in simulation. And finally, just simulation itself is not an end. It just means to an end. In the end, we want to fly a real drone. So there are some work that's happening which is targeting simulation to reality. So I'm going to talk, briefly over all these three buckets, and give you a sense of, what's happening and our work in progress. So the most mature piece is indeed the drone racing fabric. So this is AirSim Drone Racing Lab. This was developed as part of the infrastructure that was used to organize the Game of Drones NeurIPS competition. Again, it's built on top of the AirSim simulation engine. So most of the capabilities here are targeting perception and planning. I wouldn't say that we are going to low-level control here. This is still, given a very low-level controller, how can you smoothly plan a trajectory? And of course, we have the trajectory controller, but we are not really modeling at the the lowest level intricacies of a controller. This is still at the perception and the planning layer. You have the ability to create drone racetracks with gates, all of the logistics, for instance, start, stop, qualification metrics. There is a whole, study that we did on what made sense, and all those designs was intricately put by the Game of Drones team at that time. So this is all revealed through, an open source project, so the GitHub link is below, so you can go and check it out. And there's an accompanying paper as well that's going to come out at the Proceedings of Machine Learning Research. Again, the objective here is that you have to fly through all the gates in minimum time and not hit the opponent. And given that this was targeted towards machine learning and AI researchers, we introduced three different tiers. So one is the planning layer, where you exactly know the ground truth poses of the gates, as well as the opponent drone and yourself as well. Some kind of state estimation, for instance, coming from IMU. And this is really just exercise in planning. How should you plan so that you win? I mean, that's pretty straightforward. The second tier makes it a little bit more complex, where you do not know the exact poses of the gate. What you have is some kind of a noisy measurement, almost like a prior distribution on where the gate might be. But what you need to do is you need to use the first person view from the drone, and then figure out the pose and the state of the drone gate, and then go through it. So this is targeting the perception. And a lot of computer vision, machine learning people are basically trying to solve similar problems in a wide variety of areas. So it's really targeted towards them. And finally, the third tier is where you're combining both planning and perception, which is closest to the realistic scenario, where you have some prior information of where the gate might be, but you don't exactly know where it is, but you have a first-person view of image coming down. And then you have some kind of a state estimation from your drone, again through IMUs and other onboard inertial sensors, but you don't know anything about your opponent drone. So how do you then go about and win the race? Again, a bulk of this work is targeting machine learning techniques. So one tool that automatically comes out with building such a scaffolding is, for instance, an infinite imitation learning dataset generator. If you look at this video closely, what's happening is that this drone is simply flying in circle. But as it's flying in circle, what happens is that once it crosses the gate behind it gets resetted to a new position, a new pose. And the ground truth is available to you. So you can just use this trajectory to generate near infinite data that you can train your reinforcement learning algorithms or imitation learning algorithms, or any of the machine learning techniques that you want to operate and deploy at scale, for instance. Let's move on. Of course, with that, you have the ability to do domain randomization. So not just textures, but the scenes, the environments, all of those things you can basically randomize. And we know that deep neural machine learning techniques requires a lot of data. So this enables you to collect all that data in a wide variety of scenarios to train perception models, or even planning control models if you're looking at imitation learning, for instance. Quickly, the ground truth given in simulation, we have the ground truth. So things like voxel maps, sign distance fields, all of these are available through APIs that you can use. Here is a short list of APIs. I'm just throwing it out there. I won't go into the details, but you have Unreal Engine APIs that can change environments. You can load a variety of environments that's out there. Some race APIs, control APIs, and you can also customize your controller gains if you're interested in hacking those as well. So again, a wide variety of situations that you can do. However, one of the challenges that we have faced is basically the underlying physics engine, the dynamics of the system that needs to mimic real world, and it needs to completely reflect how drone racers, specifically the human pilots, operate, utilize to win these races. So this is a discussion. This is a joint work with work that's with Davide's group as well. 6 months ago, we had a conversation where we basically started thinking about how do you model, how do you build a simulator that could enable you to use maneuvers such as things like stalls, or things like gravity-induced maneuvers that a human pilot might very effectively use in order to win some of these races. So consequently, we said, all right, let's think about creating some kind of a simulations that would mimic real-world processes. And we've been looking at deep machine learning to solve some of these challenges. Let me explain why neural networks as opposed to traditional simulations using Simulink models or other kinds of physics-based models. So the first thing is that we really want to address the gap between simulation and reality. Any simulation, be it classical or neural, is going to be an approximation. Right now, if you're using classical coding to build your simulators, the only way for you to improve your simulation is to write more refined code. And that more refined code might mean that you have better estimates of your mass, of your inertia, of the physical aspects of your rotor and things like those. However, if you go via the neural network route, the advantage that you have the abstraction of throwing more data at it. I'm not saying just that throwing more data will make it perfect, but the thing is, it's possible for us to streamline a process where giving more data or collecting additional data allows us to improve encoding of the phenomenon, right? So the thing is, it is theoretically possible to achieve increase in resolution in simulation with increased data in neural sims, while in classical simulation, the only choice you have is really to do more experimentation and more refined encoding of the phenomenon, right? Secondly, deep neural networks is a generic fabric. So there are, if you look at a complex system such as a drone, there are many different aspects that needs to be simulated, from sensors to actuators to electrical circuitry to physics to laws of physics. And right now we have to write individual codes for all of these individual modules. However, theoretically, it might be possible to use the same computational fabric, which is the computational fabric of neural network, to address many of these different different modules. And this might help with scalability as well as deployment of ease in real world. And finally, if I have a neural model of my drone, of my environment, it is possible for me to use that in a model-based reinforcement learning policies, for instance. And more importantly, it's possible to increase computational efficiency. So for instance, one of our earliest experience with AirSim physics engine was that, we were not able to run it at high frame rate. The reason, because it was doing too many things like collision checks and things like those. However, having a single neural fabric, which is not not depends upon iterations, for instance, to solve complex differential equations, is it can really help us with computational efficiency. We might be able to get frame rates and physical simulations which have been unprecedented so far. So those are some of the very high level thoughts why we banked on neural networks. So let me just give you a very quick rundown on how we're thinking about what we call our work on deep simulation work. So deep simulation network is basically a collection of neural fabric that models sensing, system dynamics, and actuation. We are trying to model a complex cyber-physical system, which comprises of not just the system dynamics, but also the actuation bit and the sensing bit. So for instance, you need to simulate the entire pipeline, that that models the sensing. So for instance, I might be using cameras or lidars, or more recently, the event cameras. All of those processes needs to be modeled, and then we have some kind of a system dynamic. And more importantly, the actuation piece itself is not just physical piece. It compromises of the electrical circuitry that drives the motor. So consequently, you have all the processes such as the RC gain and inductance and capacitance that come into play. All the complexities that are associated with the delay, the lag, the hysteresis, and things like so. So there are multiple moving pieces, and there is a complex interplay of these pieces in a surrounding world that leads to a a realistic simulation. And of course, outside of the simulation is your fabric that trains a control policy. So our proposal is to use various flavors of neural networks to address many of these pieces. So for instance, you can use things like variational autoencoders to model the sensing piece, while the system dynamics piece can be done through neural differential equations and things like those. So again, just saying that not everything is complete black box. A lot of thought has to be put in while designing each of these individual components. The advantage, however, is that the underlying computational fabric is similar across all of these things. I don't have to worry about compiling one neural network differently than the others. They can actually, it's the same computational fabric. Very quickly, let's just dig into one of the blocks, which is the physics via neural ODE. So the system dynamic block. System dynamic block is trying to model the differential equation of how the system evolves with respect to an action that's been taken. The great thing is that you can actually pre-record the data from the real world, or you can have a simulator that you can try to mimic. There are many ways to do that, right? I'll give you an example of why neural ODE makes sense to do some of the modeling. So in this case, a very simple toy example of a cart pole. What you're trying to do is, instead of using the simulation equations that people have encoded in things like OpenAI Gym, you're trying to replace the entire thing with a neural network. So what you do is, on the right, I'm showing you a simple experiment where what we did was we just recorded the input and output pairs, the input being the control and the output being the derivative of the state with respect to that input. And this is a complete system. So in this case, there are no hidden variables. So here, the supervision to the neural network only came within between +1 and -1 Newton. So basically, the 3 lines that you saw is where the input to the system was provided. However, because you are modeling the entire differential neural network, the system is able to extrapolate even beyond the forces forces that were used for training. So for instance, in this case, what I'm showing you is I'm showing you the root mean square error in the position of the cart and the angle of the cart after 25-second trajectory evolution, which is quite a bit if you think about it. However, the thing is, it can easily extrapolate to the regions that the system has not seen. And this is really happening because you are modeling at the differential equation basis, as opposed to just throwing a black box of a multi-layer perceptron. So the thing is, a lot of thought needs to be put into these kinds of modules as we move forward. When we think about the drone itself, it's actually a cascade of 3 different blocks that we have decided to divide, in order to model the process. The first block, which is the block 1, is just modeling the electrical circuitry. So in comes the PWMs to the rotor, and out comes the rotor thrusts. That process itself needs to be simulated, because this is in complex RC circuitry, and depending upon the layout of your board and depending upon the layout of your electrical component, you might see different kind of resources, different kind of responses. So that is one block that basically we have as a modular neural component that gets trained. The second block basically now takes these rotor thrusts and translates them to body forces and movements. And again, this is basically a mapping. And it depends upon various aspects, such as the physical aspects of the propellers, their orientation, their placement, the body frames, and things like those. And finally, the block 3 basically takes the forces and moments and converts them into accelerations. And this is now the physics simulation aspects of it. This is basically you trying to model F equal to ma, or the Newton's law of dynamics. So the thing is, there is enough difference across these 3 blocks that we chose to model them separately, so as to give not just better resolution, but our ability to debug as well as modularize those things. So you can easily imagine that as we swap components, we should be able to swap these building blocks as well. Some very preliminary results. So for instance, the block 1, we're trying to predict rotor thrust from PWMs. You basically collect the data. Again, in this case, we used existing simulation data, but you can actually get real data and fit trajectories to it. I'm just showing you a plot that that plots the ground truth versus the predictions, and the neural ODs are extremely good at modeling these kinds of phenomena, because these are real differential equations, and neural OD is designed to model these things. Same thing with the block 2, which is a direct mapping from rotor thrusts to forces and moments. In this case, we used a simple multi-layer perceptron. This is basically, if you think, you can almost think of a table lookup, but the table lookup, it depends upon the parameters of your physical systems. So the thing is, the neural network is able to learn that. This is an instantaneous mapping. There's no dynamics involved, but again, we are plotting over the time series. The third block is more interesting one, where you're trying to model F equal to ma, or Newton's law of equations. Input to the third block is odometry and actions, and outputs are linear and angular acceleration. This is where you also have the ability to experiment with some of the recent works that's been happening in Lagrangian neural networks and other neural networks that are motivated by the physical laws. And again, as I said, this is work in progress. So I'm just going to, pause the discussion here, and I'm happy to discuss it offline if there's interest. Finally, in the last few minutes, I'll just touch upon the simulation to reality transfer aspect of it. The thing is, anything in simulation is useless if you cannot deploy it in a real world. So consequently, we've been looking at not just the algorithmic innovations. So this is a recent, collaborative work with Sebastian Scherer and his team, where when Rogerio Bonatti, he was an intern in a group. And the whole idea is that, you want to train a policy in simulation. In this case, it was imitation learning, and you directly transfer to real world. There's no tweaking, nothing. You just take the neural network and compile it down. We want to aspire towards that kind of a vision. The way we did it was basically using methods of autoencoder. So you have lots of label data coming from simulation that can help you train an encoder that summarizes the state of the drone with respect to the gate, and on which you can then train a control policy to maneuver the quad rotor. The thing is, you also want to be robust with respect to the simulation to reality transfer. So consequently, you also have the decoder layer as well, which is simultaneously trained using both simulated images as well as real world images. So consequently leading you to a representation which is much more robust. We've got some interesting results. So for instance, I'll just, in the interest of time, I'll show you some videos. So what I'm showing you, let's see if we can play. Oh, sorry. Basically deployment of these policies on real world quad rotors, where we barely tweaked any of the neural network policies. I mean, these neural network policies were trained in simulation and deployed across wide variety of conditions, right? So these are the algorithmic aspects that we've been thinking about on how to use simulation to do a sim to reality transfer. However, if you remember, as I said, I was a machine learning researcher turned roboticist. So one of the biggest obstacles that I have found is, as a machine learning researcher, it's very hard for me to come up with a hardware platform where I can just deploy my algorithms and then test it. The vision really is that you do all your development, all your training, validation, machine learning development and simulation, then you flip a bit and it goes and runs on a hardware platform. So to that, to that vision, we are basically investing again with much of the discussions thanks to Davide's group, Elia and others. So for instance, so we are working towards this vision of building a 3D printable robotic, aerial robotic platform, which will have direct one-to-one parity with the drone racing simulation work that we will do. And the whole idea here is to bring, enable machine learning researchers. It should not be limited to just a few of us who are now working on it. We really want to democratize this process where you can train and deploy policies in real world seamlessly. So with that, I'll conclude, and a bulk of all the work that I talked about is out there as open source. So you guys are welcome to check it out, send me comments, suggestions, feedback, and again, thanks a lot for our collaborators whose expertise and insights have helped us quite a bit. So thank you.
Thank you, Ashish, for the great talk. In the interest of time, we are going to cut directly to the next speaker. I would like to refer to the chat for questions for Ashish. And our next speaker is going to be Eric Cristofalo. Eric is a recent graduate from Stanford. He did his PhD with Professor Max Schwager, working on vision-based control, active perception, and 3D vision problems in robotics research. So Eric, the stage is yours.
Great, thank you for the introduction. Can everybody see my slides and hear me?
Yes, we can see and hear you fine.
Thanks.
Thank you.
Yeah, so thanks again for the invitation and to the organizers for the workshop. Unfortunately, Mac couldn't be here to present the work from our lab, the Multi-Robot Systems Lab at Stanford, but I'm presenting on his behalf some of the recent work in our lab towards vision-based perception and control, specifically for multi-robot systems. And to kind of give you a primer for this talk, we've heard a little bit about multi-robot systems today, but I'm going to kind of formalize it a little bit, and then I'm going to present two examples of cool applications that we've been interested in studying recently. And so you can think about a multi-robot system in the same way you think about a normal robot, and that's with the robotic paradigm. So if I have an environment and I have a sensor that's attached to a robot platform that can be manipulated, I might have multiple of these sensors, and following the standard robotic feedback loop, what these sensors do is they asynchronously sense their environment, maybe using vision as shown here. They process this information and do some sort of planning. This planning can be collaborative or competitive, and I'm going to show examples of both in this talk. And then they pass this information and they perform an individual control that thus closes the feedback loop with the environment, allowing them to actually interact with the world. And so some key characteristics I want to highlight here are that because we're interested in multi-robot systems, we have the ability to distribute control. So we can actually control and planning, that is. So we can actually perform our estimation and our interactions. We can do this in a distributed fashion. So we don't need to send information to a centralized source and wait for feedback. I think in most cases, this is done by sharing information on a local network. And of course, this is only possible in a collaborative setting. In a competitive setting, you might not be communicating with your neighbors to share information. And I think, like a lot of the other speakers have mentioned today, we want algorithms to be really lightweight and lightweight enough to be run on board and in real time. And I think this is a key characteristic of distributed multi-robot systems, because we're interested in robust robotic platforms. And what I mean by that is we can have many potentially cheap and easy produced robots, and the system itself can be robust to failures. So any individual failure won't take down the entire system. And these are the kinds of things we're interested in. And then finally, we've been particularly interested in vision, and that's because cameras are ubiquitous now, and the sensory information is dense and rich and fast. So it's perfectly suited for these kinds of environments. And so in most multi-robot systems, the problem is usually formulated with a bunch of sensors, and the key thing is that you don't know precisely where these are. So we don't know a translation and a rotation for each of these sensors in the environment. But what you do have in a multi-robot system is you have this underlying graph. This graph is defined by a vertex set, and this just gives a labeled ordering to each of the robots in the network. And the key characteristic is a edge set. Now this edge set can represent the communication. So these could be links for communication between nodes in your multi-robot system, but it can also represent something like measurements. So if I can sense my neighbor, then I have a sensing link, and we consider both of those cases. And again, like I've been saying, we're interested in two types of multi-robot systems. So competitive, in particular, drone racing. So we're going to look at two-player drone racing. I'm going to give you an overview of our formulation for that and our solution, and then collaborative. And there's a lot of interesting applications for collaborative multi-robot systems. And the one we're interested in lately is distributed pose graph optimization. So this is refining an estimate of all your poses in your network. This could be done in SLAM if you have multiple robots tracking trajectories over time, or it could be done with an actual fleet of robots. And so to start my talk, we're actually going to talk about just two-player drone racing. So I have two agents, maybe I and J. And the key thing we need here is the relative pose estimate. So in this case, this arrow pointing from I to J represents the relative pose estimate of J represented in the frame I. And so I don't really need to do too much motivation because everybody before me did a great job today. But I do want to highlight, this is a great example from the Drone Racing League, that you can use vision, humans can use vision seamlessly to perform these agile maneuvers. But the thing we're really interested in is actually the coordination between drones. So we want to formalize how you can use your opponents and this shared interaction between your opponents and the environment to help you win the race as the player. And so this is what we're interested in game theoretic drone racing. And so to describe the problem, I'm going to set up kind of the key features that we need for drone racing and then show you our problem itself. So we assume in drone racing we have a pre-described track. We can denote this with a series of waypoints that have positions and maybe orientations that fit through gates. This track has some specifications like a width. We know things like the tangent and the normal vectors here. We also have a drone with a position. And so for agent I, there could be multiple, but we're just going to consider two in this case. The goal is to solve an optimization that looks something like this. So I'm going to walk through this piece by piece. The first thing we want to do is maximize our position along the track. And what we're seeking to find is a trajectory that we're denoting as theta. So think of this as like a receding horizon trajectory. So we're interested in planning this trajectory that maximizes our position along the track. This is kind of the most basic thing you'd want to do to win the race, right? If you're the furthest progress at the end, then you've won. And of course, we want to do this subject to some dynamics. Here, we're just interested in kinematics of the drone in this case. There's collision avoidance constraints. There's track constraints that keep us constrained inside the physical boundaries, and of course, some control input constraints. And there's a couple things to note here. First of all, racing is a zero-sum game. This is kind of obvious and intuitive. If if your opponent wins, then you have thus lost, and there's nothing you can do. The other interesting thing is that in order to compute this optimization here, I need some information about my opponent. And in particular, I need, in this case, my opponent's position. And so this is where the real-time perception is really critical, because if I want to solve these drone racing problems in real time, really quickly, I need this really fast and quite accurate relative pose estimate, like I mentioned before. And the final really interesting thing is that the agents here are coupled through the constraints. They're not coupled through the objective, which is kind of common in game theoretic formulations. And this actually shows up specifically in the collision avoidance constraint. And it's interesting to note that, so in this case, player I cannot directly affect the position of player J in general, but it turns out that you can affect it at the Nash equilibrium, and that's what we're interested in studying. And again, yeah, just a refresher, a Nash equilibrium in this case is a strategy. So in this case, it's a trajectory for both agents such that neither agent can improve their outcome by slightly perturbing their trajectory. Now, a common way to attack these game theoretic problems is with a algorithm called iterative best response. I'm going to give you a little graphic here of how that works. So if I'm an ego agent in blue and I'm racing against an opponent, the first thing I do is I initialize my best guess of a trajectory for me and my opponent. Now, there's actually some subtlety here, because how to initialize your opponent's trajectory is actually kind of challenging, and I'll actually mention a more clever way to do this. But one thing you can do is assume there's no other opponents and it wants to go straight down the track. And what you do is you iteratively hold your opponent, you hold that trajectory, and you solve the optimization on the previous slide for your own trajectory. You then freeze this trajectory in time and you solve the same problem, but you solve it for your opponent. So again, all this computation is being done just for the ego, but I'm planning both for myself and the opponent. And the idea is if I keep doing this over and over periodically, that if these converge, they converge to something useful. And it turns out that this is a really useful way to approximate a Nash equilibria in real time. So it's computationally effective, and in practice, we've found that it often does converge to a Nash equilibria. Now, like I said, although no ego player can directly affect its opponent, that's because the opponent's position doesn't appear in the objective function. It does influence it at the Nash equilibrium. And this can be seen by, if you can imagine, if I have this opponent here, and it's actually kind of bullying my ego robot, it will affect where this Nash equilibrium outcome. Because if it's not playing the game and it decides not to move, it will affect where I end up planning, because I have these things like collision avoidance constraints. And the final thing I want to point out is that IBR actually doesn't work that well for drone racing. It works well to approximate this Nash equilibria, but what happens in practice is they're very overly conservative. And like I said before, because you have these collision avoidance constraints, what ends up happening is these robots will plan safe trajectories. So they won't really exploit these collision avoidance constraints to kind of bully their opponents out of the way. And the reason we think this is important is, aside from drone racing, these kinds of problems appear in autonomous robotic systems all the time, in particular self-driving cars. So I think there's a great video from Waymo that I don't have here, but lane merging or highway merging from off-ramps and on-ramps has been particularly challenging. And we believe that you can exploit these kinds of games to allow these autonomous cars to interact more efficiently with humans. So anyway, to get around our kind of the drawbacks on IBR, we present something called sensitivity enhanced iterative best response. And this allows us to actually influence our opponent in a way that's good for drone racing. And so I've boiled down the problem here to something a little bit more simple. So in this case, it's just, we're interested in maximizing some objective function of our trajectory. We have some constraints, and we also have our coupled constraint here that's represented as this inequality. And what we would like to do intuitively is to add this term to our objective that says we want to maximize our trajectory, of course, our forward progress, but we also want to take into account what our opponent is doing. And And actually, we want to take it into account our opponent's best response given our trajectory. So this is what the star represents. Now, it turns out that in practice, this best response given our trajectory is very hard to compute or to express in closed form. It's very difficult to find. And so the key takeaway here is that you can actually use an approximation, in this case, just a first order Taylor series expansion around the previous trajectory. And it turns out that if you do this, you can form this linearization using the KKD conditions, the necessary optimality conditions. And this comes from sensitivity analysis. And the highlight here is that it takes a form of the gradient of your coupled constraint. And recall that our coupled constraint comes from the collision avoidance. And so this is doing exactly what we wanted to do before. This is exploiting our collision avoidance to kind of bully our opponents out of our way. And so we have a paper that was recently accepted into TRO for two-player drone racing. And one of the major results is that we have a theorem for the first order necessary conditions of the Nash equilibrium. And so what I'm saying now is if you use our sensitivity enhanced IBR strategy, if it converges, so if this method, these trajectories end up resulting in one that's no longer moving, you have indeed reached a Nash equilibrium for this game, which is wonderful. And so that's all well and good, but now I want to show you what this actually looks like in practice. And so what we did is we applied this on 2 quadrotors. These quadrotors are kind of standard out of the box. We're using a kind of standard low-level controller too, where we're feeding a trajectory and then we're using an onboard Pixhawk to follow this trajectory in real time. They're flying around a 3D racetrack. So this game is actually being computed in 3D. And we've really simplified the vision pairwise pose estimation in this case. So for the kind of fast onboard perception, we have these 2 kind of silly looking spheres and we do some blob detection and using the way that spheres are projected into the image plane, using the moments, the image moments, we can estimate relative pose quite accurately in this case. We feed these estimates into EKFs that maintain a belief over the relative dynamics, so the dynamics between the 2 drones. And then since we're just planning in position, we have control over the yaw. And so we use this to track the other drone in real time. And so all of this runs in real time. The perception is done on board. It runs at camera rate, so it's about 30 hertz. And then the planning is done off board in this case. Something we've realized that wasn't apparent to us in the beginning is that the low-level architecture you want for really fast planning and perception might be different. And what I mean by that is we use an ARM-based processor for vision, which works quite well. But we found that a lot of optimization packages that we need for planning do not play nice with ARM systems, and that's why we have to do this off-board. So this is kind of something we didn't really expect at first, and it became a kind of challenging to incorporate both of these to be onboard algorithms for lightweight aerial robots. And so anyway, what we're showing here are these 2 drones that are competing. I'm going to back this up a little bit and show the green drone here. This is the trajectory that's estimated from our game theoretic planner. And we have an NPC agent up front, so he is not doing game theoretic planning. And so what happens here, this is the precise moment where the 2 drones are able to pass one another. Note that they keep looking at one another using this yaw control. And so what ends up happening is this guy simply cuts him off, right? So he bullies him out of the way using these collision avoidance constraints, and he's able to pass and then win this particular race. We did a few numerical comparisons in simulation, and to make these comparisons a little bit more principled, we did 2 sets. One where we said our technique, the SE-IBR, starts in front, it's in green, and it has a slower velocity. So this gives the behind agent a little bit of an advantage, meaning that it's always going to be faster. And so it should be able, if it can pass, it should win. And vice versa, when it starts behind, it has a little bit more speed potential compared to the person in front. And what we present is a win-loss histogram that looks like this. And so the takeaway here is that when SE-IBR starts in front, it often wins. So it wins more times than it loses. And it does this by blocking. And so these behaviors can be seen a little bit here. So what's happening is when ICIVR is rounding this corner, it's getting right in front of the MPC agent that then has to abruptly stop and continue. And vice versa, when it is behind, it wins about 1/3 of the time. So it's a little bit more challenging to pass, but when it does win, it ends up passing pretty early. And so it wins by a large margin. And that's why this histogram is offset to the right. Right? So it's pretty successful. We've looked at 2 extensions to this. So there's a multiplayer extension where we've looked at now not just 2 players, but we can reason about the intent and the trajectories of multiple agents. This took some algorithmic development on top of our original SEIVR. It's also parallelized, so it can be run in parallel to deal with these potentially many drone interactions. And like I said before, initializing this iterative best response technique is definitely of interest because it affects the converged result. And so they proposed a deep learning trajectory initialization where we've learned a mapping from robot states to good initializations, depending on where they are in the track. So this has been summarized in a recent paper by some of my colleagues. And the second is relative pose tracking. And so we've determined that precise relative pose estimate of quad rotors is extremely important to this game theoretic formulation, and that off-the-shelf techniques sometimes don't provide the accuracy we're interested in quad rotor pose estimation. And so some of my lab mates have developed this algorithm called MSL Raptor. It's an interesting acronym that actually is a real acronym. And basically, it has 2 components. It has a monocular detection front end. This can use any out-of-the-box monocular single-frame object detector. And it has a class-specific UKF backend. And so there's 2 advantages here. The first is that using this filtering-based backend, you can incorporate dynamics, so the relative quad rotor dynamics. And this is really important for quad rotors because there's a problem where if a quad rotor is pitching forward or pitching backward, the bounding box in a single image is exactly the same. And so it helps to have your dynamics built into your estimator to refine the actual pose and velocity of the object. And then finally, the estimator allows us to do slightly cheaper image processing per frame because we don't have to detect an object in an entire frame at every iteration. We can use this filter in between. And so I'll go into a little bit of details here. The high level is we input an image and we output 3D bounding boxes. And again, there's 2 components. The front end has a detector. This is, so again, out of the box, we end up using YOLO in this case because it's also pretty ubiquitous and it works quite well. This detector is done periodically and it's used to detect. There's some verification and validation done, as well as data association from previous time steps to find out which classes you've been tracking over time. This result is fed to a tracker, which then tries its best to only keep track of this portion of the image over all time. So we don't have to run this detection at every frame. We can run it periodically. There's also some tracking verification, and this produces angled bounding boxes. So they don't have to be axis aligned, but if your detector outputs those, we can use those as well. And it's fed to a multi-class UKF. So here we make some assumptions that we know something about the dynamics of our systems. We don't assume to know the control, so we assume these are kind of the baseline dynamics. And the interesting thing here for speed is that we can pass our uncertainty notion back into our tracker, both for data association and for tracking over time. And the key results here, so they compared to a state-of-the-art approach from a CVR paper in 2018. And in their implementation, it's a factor of 3 times speed up, so it runs quite a bit quicker. And for these quad-specific scenarios, so, they get a pretty significant translation and rotation error reduction when they're tracking over time. And so I want to show you a cool video that they've compiled of what this looks like. So again, we know something about our robot. We require a detection network that provides the initial image-based detection. And we have to know something about the physical object. We need to know its scale, basically. But this is pretty reasonable for drone racing. And so what I'm showing here is a video where this is all done on board. So they have NVIDIA, it's a Jetson TX2. There's a global shutter USB 3 camera. And what you're seeing is, this is the result of the, so this is the bounding box that's fed to the estimator. And what happens is this front end sometimes loses track, right? So it doesn't detect the correct quad. And we can use the uncertainty from the filter to feed this back in and to reinitialize the detector, basically. And so the high level takeaways is that for this room, this quad rotor is flying from 0 to 10 meters in front of the camera. And on average, the translation errors are about 0.8 meters and rotation errors are a little bit less than 9 degrees on this tracking. So this is super useful. And we haven't yet integrated this with our drone racing result, but we hope to in the future. Let's see, I'm coming up on time soon. And so I just want to highlight the other side of the coin. So I talked about competitive scenarios. And so I really want to briefly mention just a quick application of a multi-robot collaborative example. And so I mentioned these relative poses along individual edges. But in reality, when you have a multi-robot system, you'll have these poses that are going kind of in all directions, right? And if you gather these noisy poses over your entire network, you might want to use this information to refine the poses of of all robots in your network. And I note here that these measurements are not often consistent. And what I mean by that is you can think of them as they're not equal and opposite, right? They're corrupted with noise. And what I'm describing here is pose graph optimization. The goal here is to estimate these poses by minimizing some sum over all your edges in your network of a translation and an error rotation term. And so what I want to present really quickly is that we propose a consensus-based way to do this in a distributed fashion. And so it ends up being really cheap and computationally efficient for multi-robot networks. Yeah, for the sake of time, I'm going to skip forward a little bit and just show you these consensus-based techniques that can be applied kind of out of the box. So if you're familiar with consensus, this is a pretty common technique. And the idea is you provide some aerodynamics for your translation and your rotation estimators. And so we provide two flavors, an axis angle and a rotation matrix version. And there's also a coupled rotation component. So the idea is we're estimating poses in SE3 in real time using these techniques. And because it's consensus, we're kind of leveraging this control technique for estimation. And I'll note that these are nonlinear and non-convex estimators. And the key takeaway is that we use some tools from Lyapunov theory to make formal guarantees. I won't go into too much detail, but the high level idea is that we give necessary and sufficient conditions on what these noisy measurements have to look like for distributed estimators like this to converge in practice. And so I'll show you a little bit of what that looks like. So if you achieve these conditions that I mentioned and you run our estimators, so these are graphics of the estimation evolving in a distributed manner. So note that one robot is responsible for estimating the poses of each of these little systems in the network. And so the idea is that they reach consensus very quickly. And when compared to state-of-the-art approaches, in particular SE-Sync, which is a centralized certifiable method, the key takeaway is that we don't quite reach the global minimum because this is a gradient-based approach, but we get very close in 1/5 of the time in a distributed manner. Yeah, so we applied this to a multi-robot system where we use structure for motion to estimate these edge pair links. And the key takeaway is that we can do this in real time and it's really efficient. And so with that, I want to thank again the organizers, and I'd be happy to take any questions you may have. Thank you.
I think we'll have to push the questions again to the chat, if you don't mind. And I'd like to introduce the next speaker. Our next speaker is Philip from the University of Zurich, who's also one of the organizers. Philip works on agile autonomous drone flight and specifically the co-design of estimation, planning, and control. I'll give it to you, Philip.
Thank you, Varun. Can you see my screen fine?
Yes.
Perfect. Okay, so thanks everyone. I'm gonna show some recent research of ours on time-optimal trajectory planning for quadrotus. We have heard quite a lot about agile flight in this workshop, but actually, unfortunately, no autonomous system really is as agile as humans. Humans can be insanely good pilots. They have extremely robust visual perception, and they can iteratively learn when flying a track. They can improve on their last lap and make better and better times. But what if, just for a second, we assume that robot perception was on a human level and state estimation was no longer a bottleneck? Or what if human pilots want to become faster and want to know what would actually be the best trajectory to fly? We arrive at the question of how can we plan time-optimal trajectories through a sequence of waypoints? And state-of-the-art research has done this using polynomial trajectory planning, which generates smooth trajectories, but suffers from some drawbacks, as we will see later on. On the other hand, there is numerical trajectory optimization, which discretizes the trajectory in time. However, if we want to pass multiple waypoints in such a trajectory optimization problem, we actually need to allocate these waypoints as costs or constraints to specific nodes in time. And we do not know this allocation beforehand. So that makes the optimization kind of very influenced by our initial guess or by our time allocation. Let's take a step back and look at what's actually the limiting factor in flying fast trajectories with a quadrotor. A quadrotor has 4 independent thrust inputs. If we apply a differential force, we can actually cause a body torque and generate some rotation that allows us to align the acceleration direction. However, our 4 actuators are limited. They have a certain minimum and maximum thrust they can apply. And we can reformulate the thrust into the collective thrust, and this is the body C direction acceleration that we can get, and the 3-dimensional torque around the body. So to be quick, we need maximum acceleration, but we also need it to face in the right direction. And to actually align our acceleration direction, we need to rotate, and therefore we need some torque. However, every time we apply torque, we need differential forces, right? And so when we are already applying the maximum thrust at each rotor, the only way we can generate differential forces is by lowering some of the thrusts. Therefore, when we want to rotate or change our rate of rotation, we actually need to limit our linear acceleration that we can have. And this renders this problem, or this renders the quadrotor, an underactuated system with input constraints, where actually the reachable input space for acceleration and torque is coupled. Now, polynomials are sometimes suboptimal. They are describing decoupled axes. And this is very efficient to plan, actually, but it renders the true input limits very difficult to apply. And polynomial trajectories actually enforce smoothness, which facilitates tracking. But on the other hand, it renders the input change rate dependent on the time scale. And it often limits the input change rate to values lower than what we could apply on a quadrotor. So we want to tackle this problem with trajectory optimization. We formulate this by using our quad that should pass a bunch of waypoints. To find the trajectory through these waypoints, we discretize the trajectory, and we can enforce the system dynamics, the input constraints, we can fly through multiple waypoints, but as I mentioned before, we have to allocate our waypoints to specific nodes along the trajectory. This allocation is unknown a priori, and therefore we need to somehow find this allocation. But we don't know the trajectory yet that we're going to fly, so it's a bit of chicken and egg problem. So instead of allocating these waypoints to specific nodes along the trajectory, we actually formulate a measure of progress along the trajectory. We formulate this measure of progress individually for each waypoint. And then we want to track this progress, and we only allow the progress to change in close proximity to a waypoint. This allows us to simultaneously optimize the trajectory and the waypoint time allocation. So how does this work in detail? First, we discretize our trajectory, and our trajectory consists of some states and inputs. The inputs are applied over a certain delta time, and this delta time is dependent on the total trajectory time. In our case, this total trajectory time is actually part of the optimization variables, together with our states and inputs. The system dynamics are enforced with a quality constraint between the states, and the system's input limitations are a box constraint. Finally, we can optimize our trajectory for the minimum time. So how can we enforce it to pass through waypoints? Let's imagine we have two waypoints that we want to pass within a certain tolerance. Now we formulate our progress variable. Here, lambda1 for our waypoint 1 and lambda2 for our waypoint 2. These progress variables are 1 at the beginning and 0 at the end of our trajectory. 1 corresponds to indicating an incompleted waypoint, whereas 0 indicates a completed waypoint. The progress variables actually evolve along the trajectory over a variable mu. And we can now tie this variable or constrain this variable to only allow change under certain conditions. So for our time allocation problem, we use a complementarity progress constraint. This means that we formulate a constraint between all the states and the waypoints. And whenever a state is further away than our tolerance, it should not be able for the progress variable related to this waypoint to be completed at this state. We do this by formulating a constraint on the distance of the momentary state from the waypoint, together with the slack variable for its tolerance. Now, this expression is non-zero if we are too far away from the state, and therefore our complementary expression here, the progress or the evolution of our progress, needs to be 0. However, if we look at the state close to our waypoint that is within tolerance, actually the expression here in the bracket can become 0, and therefore our evolution of progress can be non-zero. This means that this waypoint at this state can be marked completed. If we look at the trajectory, it looks a bit like this. So we have lambda2, which until our waypoint 2 is marked as incompleted, and from here on is marked as completed. And the same goes for lambda1 for our waypoint 1, which after state 3 is marked as completed. So with this, we are able to actually optimize the trajectory and the time allocation problem at the same time. Now, we want to evaluate this in kind of a bottom-up approach. We start by just looking at a very simple scenario. We want to fly a straight line, and we have one setup where we evenly distribute some waypoints along a straight line. In the second setup, we have our waypoint squeezed a bit to the beginning of the straight line. Now, we would expect to get from the optimization exactly the same solution, because it doesn't really matter where our waypoints along this line are. And in fact, this is exactly what we get out of it. So we get a solution that has a equal total time in both cases, flies the same trajectory, uses the same inputs, which furthermore are kind of like bang-bang inputs, where we only spend a little bit of time away from the maximum thrust at the beginning to introduce some rotation. But then we spend all the inputs fully at the maximum or at the upper limit of what's possible to accelerate as fast as possible along the trajectory. And we get this exactly the same way in both scenarios. The only thing that is different is how our progress variables indicate the progress along the trajectory. So in one scenario, our progress variables flip from 1 to 0 to mark a waypoint that as completed at specific times corresponding to these waypoints. But in the other scenario, they flip at different times because we have a different distribution of these waypoints. Now, we can go one step further and ask the question, well, isn't that probably very initialization dependent? So we did a bit of convergence analysis on a scenario where we fly from an initial condition at the top left here to a first waypoint on the right-hand side, back to a second waypoint on the left-hand side. The red line here is our initial guess. And we set up a second scenario where we want to fly the same waypoints, but this time we have a poor initialization guess that actually skips waypoint 1 and goes directly to waypoint 2. Again, even if we provide this initialization to the optimization, it finds exactly the same solution, taking 3.6 seconds in both cases, and arrives at the dark blue or blackish trajectory solution here. However, it takes some additional steps to reach this solution. So we also applied this to some larger scale racetracks. One prominent one is probably one of the racetracks from the last year's NeurIPS Game of Thrones challenge in the air simulation. This is here on the right-hand side, and this is the qualification track number 1. And on this track, the best team in the competition actually reached a time of around 30 seconds. This is actually quite fast already. However, if we feed this track into our optimization, it will generate a feasible solution that passes the whole track in only 24 seconds. This is around 20% faster than what the fastest team achieved. Now, we also performed additional evaluations comparing our work to other state-of-the-art approaches. We also investigate the behavior of non-convex formulations under different initializations. And we even give a qualitative comparison to some human-flown trajectories. But all of this would probably go a bit past the time of this presentation. And therefore, I would like to mention that this is all going to be in an archive paper coming out later today or probably tomorrow. And it's called Complementarity Progress Constraints for Time-Optimal Quadratic Trajectories. Now, our approach is capable, given an accurate model, of generating truly time-optimal trajectories that are feasible for quadrotus and respect and also exploit the actual actuated limits. However, there are several open questions that we have right now, which go over efficient problem formulations to convexity of the problem, convexifying the problem for certain scenarios, or deriving guarantees for the optimality of solutions. We also want to ask the question whether the full time horizon needs actually to be respected in planning something, or whether we can arrive at very similar solutions when only planning over a subset of the whole track. Then one very interesting part is how accurate are our models and how can we model aerodynamic effects, and how can we trade off speed against robustness so that we actually can execute these trajectories on real systems. Because if we spend all the time at the actuated limit, there is really nothing left for robustness. And with that, I want to thank you very much for your attention, and please check out our upcoming paper. Now, Varun, do we have some time for questions?
Yeah, we can take one question.
If there is one.
Okay, I think let's move.
Okay. So then I will go right ahead and introduce our next speaker, which is Varun himself. Maroon is a PhD student at MIT, advised by Professor Serge Karaman, and his research interests are on computationally efficient state estimation and planning for high-speed navigation.
Thanks for that. Let me just share screen real quick. Oh, sorry, I need to restart Keynote. Okay, let me do it this way. Wait, let me present using Keynote. Can you see my screen?
Yes, we can see your screen.
Okay, so I'm going to present this way because for me, it kills my Zoom session when I go to full screen. So my talk is titled Computationally Efficient Perception-Aware Planning for High-Speed Flight. Just to give some context, I think a lot of people in this call have given great context and great motivation for this, but just to reiterate, the idea is for us, we want to be able to follow some sort of predefined path in a robust fashion and also in the shortest time possible. So if you look at the picture, you see a drone and there's a little path that you want to follow. And then there's some landmarks in the environment which are considered critical, and we want to be able to see those while we're executing the path. So let me take a quick step back and motivate why, for me, this is an interesting problem, and sort of why we're also saying, we want to be going towards this idea of autonomous super vehicles. So for me, autonomous super vehicles are ones that can navigate extremely unstructured or extremely dynamic environments at least operational speed, and ideally much, much faster than human piloted vehicles. So this is an example of a forest where you have a drone flying around, and this is a fairly challenging perception problem because it's unstructured, and also doing obstacle avoidance is hard because you don't really know what new things have changed in your map, etc. Another probably motivating example is, you have a drone pilot who is taking aerial videos of these cars, which is great because you can get pretty close to it, but this would still be something that's fairly scary to do autonomously, especially when you have close interactions with other moving things or moving people in the scene. So just to recap, I think I showed this video before, but this is kind of the state of the art of the drone racing league. This is a human pilot who's flying through these pre-recorded courses, and I believe the speed here goes to about 16, 17 meters per second. In contrast, this is from IRAS a couple of years ago, and the reality of current autonomous drone racing in a lot of cases has still been around the 1 to 2 meters per second, maybe with the exception of some of the Alpha Pilot contestants last year. So let me take a step back again. So these are some videos from the Alpha Pilot Challenge. Some things that are interesting for us was, so there is a gate right at the end. This gate almost never moves, and a lot of people went with forward-facing approaches to these gates, and then try to, as soon as they finished one gate, they would try and find the next one. But there were some that were that tried more interesting maneuvers, let's say, like this one, which completely flips, assumes that the next gate is known, but tries its best to already point in the direction of the gate before it has to make that sharp turn. So in terms of related work, there's quite a lot of related work in this area. There's quite a few approaches that have looked at this sort of time optimal path parameterization for robots. A lot of this approach has like historically been focused towards manipulators and robotic arms, which are also high dimensional problems. And recently we have a couple of works that also extend this to quadrotors. As Philip mentioned, there's been a lot of work on using differential flatness and polynomial trajectories for planning. I think the most commonly used approach is the sort of min-snap approach brought out by Malinger and Kumar, and also Richter et al. There's a few approaches in this intersection, which is both perception aware and exploits the differential flatness of the quadrotor planning problem. And of course, there's work even from Dr. Scaramuzza's lab on the sort of perception aware model predictive control and things like that that also solve this perception aware planning problem. So just to be a little bit formal, the problem is we want to be able to minimize the time subject to some perception constraint. We also want to be able to obey the dynamics of the robot and of course the actuation constraints of the physical system. So for me, one of the perception constraints that I personally thought was motivating and wanted to push was the idea of co-visibility. Now, so in this function, you can see that the weights are some sort of human-tuned parameter trying to enforce which landmarks are more useful compared to the others. The function V takes in the camera poses at different times and the landmarks and acts as an indicator of whether they're visible in the frame or not. And of course, we have a time penalty for the actual quadrotor. Our initial sort of approach was to put this into a sort of Gauss-Newton kind of optimizer and just do gradient descent on this. But let me also explain why co-visibility constraints and why that was the approach that we took. So if you look at these blue triangles, they represent poses in the sort of path. And then you have a star, which is the landmark. Now, the idea is that if all of the poses can see the same landmark, they have a common frame of reference, and this adds to your pose graph and adds a strong measurement. So in fact, like in a lot of state estimation, having longer tracks can correlate directly to how robust your system is and how well your full estimation pipeline is running. So for this approach, like I said, we were trying to use a basically sort of gradient descent kind of algorithm. So we proposed an indicator function that's soft. Normally people use something like a conical model to approximate the camera frustum, but we try to come up with a function that's truer to what a real camera frustum looks like, and yet differentiable, so we could put it into this gradient descent framework. So just to show some of the results from that work. So this is one of the flights that we did, and this has no perception constraints. You can see it's spends a lot of time looking at these sort of blank, untextured walls, which is of course poor for state estimation. And in fact, you can see that this is the plot of the motion captured track after the experiment. And you can see that it deviates quite a lot from the pre-planned path. In contrast, this was one that was generated by our algorithm, which is perception aware. And you can see this is crisp. So some of the results show that, at least preliminarily show that as we increase the speed, the robustness is also kept. So you can see that it's quite crisp. And for details of the paper, we published it at the American Control Conference last year. And if you want to check it out, please do. So moving on, I think, so one question that we left open from that paper was also this idea of we were still tuning these trajectories to balance out the perception constraint and the time optimality. So one thing we wanted to explore was, could we also make some stronger claims about the optimality of the actually chosen path? So I'm going to review here an algorithm that was proposed by Pham et al. The idea is simple. The idea is you proceed backwards. So you start at the final node, and then you compute backwards the computable sets. So one thing to note here is that we use the speed squared, and previous work has shown that speed squared is actually a nice proxy to a minimal time problem. So maximizing the speed squared profile minimizes your time. And then the idea is, once you've done the backward pass and computed all your controllable sets, you start at the initial speed that's desired, and then greedily choose the maximum control that keeps you in those sets. So you proceed forward, and then in the output, you have a path. Now, what's interesting here is in our LTSS paper, we were able to show that this algorithm is, in fact, asymptotically optimal in the number of discretization points. So traditionally, a lot of people also take a convex optimization approach to this sort of time optimal path parameterization, whereas this uses the discretization points, so it has the computational, has the computational efficiency, but also thanks to some of our proof, we can also say that this is asymptotically optimal. So then we extended this work back onto the quad order scenario. And in the quad order scenario, we take in as an input the path and the selected landmarks in the thrust bounds from an algorithm such as the one I described before, like the one that we presented at ACC. And the idea is that you now already have a parameterized path in the translational space and the yaw. So we're not selecting those things, but we are selecting the time at each point. So then we first solve the time optimal path parameterization problem, like the one, using the algorithm that I just talked about, with the additional field of view constraints. So in this case, we do model the field of view as a cone. And all we want to do is we want to keep the selected landmarks inside that cone at any point in time. But in the first pass, we assume a point mass model. So we don't assume the full dynamics of the quad order. But then we get the one limitation about this algorithm is the output rotations are not necessarily smooth. So we can't directly pass this to a quad order. Like we cannot use an off-the-shelf, INDI or PID control mechanism that assumes that these control inputs would be smooth. So what we do is we smooth the output, the rotation vectors, with a Gaussian filter. And then now we assume that the smooth rotations are fairly close to the rotations that we got out of the first step. So from there, we then solve the time optimal path parameterization again. And in this time, we again include the field of view constraints, and we also can now enforce a bound on the physical motor thrust. So we can actually enforce a bound on every individual motor. And this is then fed back into like a traditional state-of-the-art trajectory tracking controller, and we can track this trajectory. Just to show some of the results, so we recently presented this paper at ICRA, and some of the results here is we're showing like a simple slalom trajectory and multiple landmarks in the environment. The algorithm does not make any assumptions on the number of landmarks and things like that. Of course, the distribution of landmarks might make your speed slower based on how your field of view constraint works. Here's another example of an actual experiment that we did in the flight control lab. And you have this blue dot, which represents the landmark right in the middle. And the trajectory has to follow some sort of circular loiter, but with the input constraints and things like that. So one thing that I would like to quickly highlight is if you look at the squared speed profile, then the actual quad rotor can follow the speed profile quite accurately, even at higher speeds. It's noisy because the noisy measurements are from the motion capture, but you can see that this is still pretty accurate to the planned squared speed profile. So what we want to kind of say here is, although we're still hitting about 4 or 5 meters per second, this algorithm is still close to the bounds, and we're also able to say that it is possible for the generated trajectories to be followed by some sort of state-of-the-art trajectory tracking controller. With that, I would like to take questions. Okay, I'm probably going to assume that there are no questions, and maybe in the interest of time, we can move to the next speaker. Our next speaker, yeah.
Or if it's not too late, a very quick question. I missed a little bit of the beginning of the talk, but can you just, is the perception constraint just geometric on the field of view, or do you have any maybe thoughts or comments on how to see it? Even if, imagine you, in two cases, something is in your field of view, but, maybe it's at the corners of the field of view, or somehow, I'm wondering if there's a second level of representation on top of the landmark probabilistic one, or some other type of information that can enrich the cost function?
I think that's a good question. So in the first case, of course, you can be closer to the end of the view frustum, simply because the indicator function is non-conical, right? But in the second case, there's sort of, if you look at the angle of the cone, the amount that spreads out, we can control how much you want to be away from the periphery of the camera, if that makes sense. So that's one thing. And the other thing is, in more recent work, we've also considered the problem of selecting features. So you can actually, that's a paper that just got accepted to IRUS. And in that paper, we do also think about other things like the strength of the feature, or more specifically, things like what speed profile that particular feature would induce on our trajectory. Does that answer your question?
Yes, thank you.
Okay, I think let's move to the next speaker. Our next speaker is Professor Walterio Mil-Coes, the professor at the University of Bristol. His research interests are robotics, wearable computing, computer vision, and he's been focusing on algorithms operating with limited computational sensing and power resources. With that, the stage is yours.
Thank you very much. Can you hear me well?
Yeah.
And are the slides coming through okay?
Yeah.
Okay, thank you. So I am going to talk about this project that is part of a collaboration between the universities of Manchester and the University of Bristol. And this is funded by the UK EPSRC. And this project that we internally call Agile is aimed to try to link perception and action. And to do that, we're doing this with a new type of device, which is a pixel processor array, and specifically the SCAMP architecture. So let me just describe in very general terms how we normally think about a standard vision system pipeline. And I know, let's say Guido and Skydio already mentioned alternatives to these standard pipelines. But in general, when we're thinking about how we're going to proceed for a robot, we think that we have a sensor that has to go through a number of steps. Let's say an analog to digital converter, and then we have an interface that allows us to send lots and lots of information in the shape of images to processing units. And perhaps this processing unit needs some extra support in order to make further computations. Perhaps we use a GPU that is in close communication with that CPU. Eventually, we can go to a microcontroller and then to a motor controller. So is this the way in which we should think for the future of agile perception robotics? I think I'm preaching to the choir here, because I think this type of visual perception and processing pipeline is not ideal for us to try to do what we really want to do in terms of agile perception. So what are the alternatives to this? One of them, and this is precisely what our Agile project is aimed to develop, and this architecture, the SCAMP architecture, has been developed by my colleague Piotr Dudek at Manchester University for a number of years. It's an alternative to this standard processing pipeline. In a pixel processor array, which is a generic term for this architecture, what you have is, for every sensing element, so a pixel has a full processor next to it. So you have an ALU, you have registers, you have input and output communication with neighboring processing units, and therefore you can have a parallel sensor and computer module that allows you to do computation at the very same time you're able to capture images. So the SCAMP PPA, the SCAMP 5, which is the generation that we're using in this project, has a 256 by 256 processing elements, and allows us to do many things without having to require external processors and the interfaces and the protocols of communication that delay action. So with a SCAMP processor array, essentially what we can have is directly from the sensing and processing element, we can go into lower level interfacing with the action that needs to happen. And so instead of sending lots and lots of images in a wasteful way, the SCAMP PPA can send very high level information, perhaps the direction that we need to follow, the speed that we are traversing or that we need to traverse. We can even do things like classification and localization of targets. So instead of sending wasteful information, we are already processing what is relevant and sending this information into these lower end computing devices, perhaps directly, as we have also done in another experiment, directly generate control signals that go into the motor controllers straight away. So with a SCAMP, with a PPA, with a pixel processor array, we hope to make this transition from perception to action as close and as tightly as possible. And indeed, SCAMP belongs to a long family of neuromorphic vision sensors, of which one of the most well-known is the event cameras that, let's say, the group of my colleague David Escaramuza has significantly advanced from the point of view of vision and perception for drones. But with a SCAMP, we can do beyond that, beyond the detection of events. We can essentially, because of the way in which the processor and the sensor is coupled together, we can start to do high-level things. We can detect features beyond events, like salient features. We can detect objects. We can compute speed. We have done visual odometry and things like that. So with a SCAMP, for example, and let me see, is this video coming through okay, by the way?
Yes, it looks fine.
Some of these videos. So this is an example of SCAMP running at about 1,000 frames per second, and this is mostly limited by the available lighting indoors. It can go well beyond that, detecting salient features. So it's not just events, it's actually salient features. So you can, instead of outputting images or events, we can actually compute features and provide the exact location of these salient features. But perhaps more interestingly, within this project, we have started to explore many other things that are relevant to Agile robot navigation. So we have an IROS 2017 paper where we use a SCAMP to track a moving vehicle that is following a chaotic trajectory. So there are unpredictable reversals, and the drone has to keep track of this device, and everything is happening on board. So this was an early demonstration of having a target tracker fully on board of SCAMP. Then we have an ICCV 2017 paper where we have implemented visual odometry, where essentially we can estimate how the camera is moving in space, and then eventually compute a trajectory that the camera is following, and everything is being done at the time the images are being captured. So on the image plane, applying some computation there, we can output visual odometry straight from the device. And more recently, and you might have already thought about this after seeing the SCAMP diagram, the PPA architecture is ideal for applying deep networks, because we have a parallel array of processors, and in this case, this is an ICCV 2019. We have a demonstration of having the detection and tracking of a moving object with a deep network implemented fully on the SCAMP device. Now, what is different from the point of view of this pixel processor array and other efficient architectures that we can consider for Agile robotics? One significant difference is that this is a general device. So the same device with minimal programming, and sometimes on the fly, we can just change the program and do a totally different task. So we can be running a CNN that is running car detection. We can be running visual odometry simultaneously, or a staged but very fast speed of switching, or target tracking. So this device is a general computing device that is much closer to that dream of having perception and issuing of actual commands. And the topic of this talk is indeed how we have started to apply this to the case of drone racing. So inspired by the course track from IROS 2018, so we have set up an indoor flying configuration here, where we have these gates through which we want the drone to fly. And our objective here is to have the drone go through these gates and use a SCAMP. This video that I'm showing at the moment is not using SCAMP, it's using the Vicon, but it's an illustration of how we can navigate through this space. And what are the challenges that many of the different compelling challenges that an Agile drone will have to face when you have to do this? In this case, we think that we have a slightly more complex configuration than in some of the competitions or illustrations, because we on purpose are having multiple targets that may appear on view. So the drone actually has to make a decision about what is the gate that it has to follow. And we want to do this visually as much as possible. So in this case, we're just illustrating that you can have on the same view, apart from the radial distortions of the camera, you can have multiple gates that are in view. And you have also very acute viewing angles that you also may need to face. So there are several challenges here from the point of view of the visual processing, and also motion blur and so on. So the way in which we have implemented this is that we have the SCAMP pixel processor array system that in this case is communicating with an Odroid. The Odroid is really just for ease of prototyping. There is no need to have an Odroid here. So indeed, we have done experiments where we issue the actual pulse width modulation commands directly to motors. But in this case, for illustration and prototyping, we have an Odroid there, and we have a Pixelhook flight controller and a quadcopter. And everything is living within motion capture system, mostly for geofencing and also for some velocity estimate. So the SCAMP is, in this demonstration that I'm showing here, not estimating the full state of the robot, but is the step that we want to take next. So we have a Vicon system that provides this geofencing and velocity estimates. We're not using any IMU information. Again, this is on purpose, just to try to emphasize what can be done with the visual processing on its own. And importantly, we have this perception-aware motion predictive controller that allows us to combine the information of where we roughly expect to have the appearance of these gates that are then refined from the actual inputs of the perception from the drone. And the algorithm that we have in there is running at more than 500 hertz, maximum 1500 hertz. And it follows a very simple approach, but again, it's a generic computational module. So we can, in principle, change this algorithm on the fly or very quickly. We have actually used this algorithm for target tracking before, and it's essentially following a flawed algorithm. So essentially, the way this works is this is the input image. We invert this image, and then we fill the remaining closed shapes that appear in there. And then we subtract these from the input image, and we end with one that allows us to predict 4 corners that we estimate the gate is at. And then we fill this form, and we subtract these 2, and we end with an estimate of where the gate can be. And the remaining pixels here are an indication of how good this estimate can be. And we're mostly trying to find the closest gate to where we are. And therefore, this allows us to, in the case of having 2 gates in view, generate a result that, compared to this, will tell us which one of these 2 possible corner configurations is the most appropriate. So we have an IMAV 2019 paper that describes this in more detail, and also for the videos, in case they don't play very well, and all the other papers I have mentioned, you can go to our project website, which is project-agile.org, where you can find more information. But essentially, the vision that is happening here is very simple, but it can work very well in parallel for this architecture, and we can use it for the drone racing. So in this case, what you see here is a simulation of how we're using the perception-aware model predictive controller to navigate this drone through this space. And one thing to note is that we have also, on purpose, made the location of gates to be uncertain. And this location needs to be refined by the perception of the drone as it navigates. And this is why you're seeing some of these gates initially are in a location which is not the final location, but this location is refined, and that location is used by the drone. And this is actually what the drone perceives. Because of the way in which the scan works, we essentially do not record all the images. That slows down computation. But we record some of them in some cases like this so that we can actually illustrate what is going on. But the scan is not a pipeline designed for recording images. And I think this is actually an important highlight. The visual sensors that we normally use in robotics have been designed for purposes like recording images. And that is not necessarily what an Agile device requires. So we actually struggle to record images with a camera. But because this camera is a very special one that is designed for processing. And this is like an overview video where we have the drone actually navigating through these gates using the model predictive controller and the scan. And as you can see, there is quite high acceleration happening. So because of the limited space, the speed is not something that we're emphasizing, although this is running at 2.3 meters per second, but it's the high accelerations that we have to cope with. And in part, we are able to deal with this because of the high frame rate of the perceptual device combined with the model predictive controller that we have. And this is an illustration of the level of accuracy that we can achieve. So if you think of this frame as the actual gates frame, we have 1 meter square. And these trajectories here are essentially the average of how the drone is going through these different gates. So you can actually encase for the different gates over a number of trials in a box of around 20 centimeters by 20 centimeters. So the accuracy that we can achieve because of that final refinement that is happening from the visual perception combined with the controller, we can achieve this level of accuracy that will allow us to fly through a much smaller, narrower gate. And one extra modification that we are also considering is, I already spoke about our intention to be able to refine close to the position, the location of the gate, but what happens if the gate is actually dynamic? So we have another experiment where the gate is actually an oscillating pendulum, and the drone actually works with that information. And in this case that we have started to experiment, we fit a model of the pendular motion, and the drone is actually able to go through the gate after the perception of how it is moving. So to conclude, and also in the interest of time, with this new type of sensors and processors designed for Agile perception, I think we are entering into a very interesting era in terms of Agile robotics. And if we can use this new opportunity to create new devices that can react agilely to the environment, then we will be able to materialize much simpler those dreams of drones being able to really deliver in a complex and certain world. So the next steps is we're working, our colleagues in Manchester are working on smaller versions for the SCAMP architecture. We also want to have a tighter integration in terms of the perception and the controller, perhaps being less conservative, because in the space that we are working, being small, and also the fact that we don't have many SCAMP devices around, we are relatively conservative in how aggressively we're flying these vehicles. We want to deal with higher uncertainty. And also, this is something that we're also investigating. We're working on an application for this, we're also aiming to combine multiple tasks being performed by the same perceptual and action processor, like computing the visual odometry that we have presented before with the gate detection or target identification, perhaps as part of some CMMs being implemented. So again, I recall that our project page is there, and one of the objectives of our project is that we hope that soon we're going to issue a call for giving SCAMP devices, SCAMP hardware, to collaborators around the world, so that people can actually start using this new type of visual processor device. So keep an eye on there, and I am happy to take any questions.
Thank you very much. I think in the interest of time, we're going to cut to the next talk.
Okay, thank you.
For questions, I would like to refer you to the chat. You can always ask questions there. I think everyone has access to the chat. So our last talk is by Miguel Fernandez Cortizas and Carlos Redondo Plaza. And Miguel and Carlos are from the Polytechnical University of Madrid, more specifically from the Computer Vision and Aerial Robotics group. And they will present a short paper related to the Alpha Pilot competition. So without further ado, Miguel or Carlos?
Okay, yes, I'm going to start. Is everything okay? Can you see the slides?
Yes, we can, thank you.
Okay. So thank you very much for the presentation. Good evening, everybody. So as you have said, we are Miguel Fernandez and I'm Carlos Redondo, members of the Computer Vision and Aerial Robotics research group from the Polytechnical University of Madrid, and we present our approach for Alpha Pilot Challenge. So autonomous racing drones are currently far from reaching human performance, so its improvement is a challenging research field in autonomous perception, localization, navigation, and control of drones at high speeds, as well as using onboard computers, what forces to use lightweight algorithms in order to achieve real-time performance. So in this talk, we present a complete framework based on the Alpha Pilot Challenge, which has already been presented. This is an autonomous drone racing championship organized by the Drone Racing League and Lockheed Martin, with a grand prize of $1 million. So this competition has two virtual qualifying tests before the real flights. So the first one consists on achieving the best possible gate detection algorithm, accounting for both precision and time consumption. And the second one, on which we have focused, consists of autonomously completing a simulated drone race circuit as fast as possible, in which an approximate location of each gate is previously known with certain error. So Flight Goggle Simulator is the one used for this test. So it has been used for developing and testing the flight performance, and all the results presented have been acquired in this simulator using the default parameter configuration. So the system to solve the above-mentioned challenge has been divided into 4 different modules: the perception, state estimation, trajectory generation, and control. And we have focused on 2 possible improvements, one of them in the state estimation process and the other one in the trajectories generation. In one hand, a semantic SLAM algorithm using the gates of the circuit as landmarks has been implemented to optimize the visual inertial odometry estimation, reducing the drift error. On the other hand, the trajectory generation has been divided into 2 different parts: a long-term path, which allows to update the path of the whole track, and a short-term trajectory that provides fast reaction to path changes with optimal control actions. So in our approach, we have decided to use position-based visual setpoint, which requires an accurate estimation of the position of the gates in the circuit in order to pass through them by making corrections in the trajectory. And as we can see in the video, the corners in the image are given by the simulator. Moreover, in this competition, the size of the gates is standardized, which allows to apply a perspective endpoint algorithm to the corners of the gates seen by the camera. So once the estimation has been made, a 2-step filter is carried out. In the first place, it is checked that the new measurement is within a confidence region And in the second place, this new estimation is weighted so it does not cause sudden and sharp changes in the trajectory and therefore yielding to likely future control failures. So in this video, we can see the PMP estimation along the circuit. Then for the state estimation module, a visual inertial odometry algorithm has been applied, which allows us to estimate the pose of the drone when no gates are visible. The combination of both camera and image sensors is very appropriate for achieving robustness in state estimation. In one hand, the IMU provides robust measurements even at high speeds, but accumulates drift error over the time. And on the other hand, the visual odometry allows to minimize the IMU drift error, although at high speeds, motion blur impairs the precision of its measurements. So different approaches such as robust VIO and Vince fusion have been tested looking for the best results. Finally, Vince fusion has been chosen because it can provide higher accuracy, maintaining a low computational cost. This algorithm is based on a corner feature detector using a brief descriptor for matching, and finally applying Canard-Lucas stochastic for tracking those features. So in the video, we can see the Vince fusion estimation as well as all the detected features. And then, even though the VIO enables self-localization, we have taken advantage of the gate pose estimation with the purpose of improving the VIO so that the next gate is reached with the minimum possible error. We have adapted the semantic SLAM algorithm developed by Bable et al. To use the PMP estimation. So the drone state vector is propagated over the keyframes, while landmarks are set by the position and orientation of each detected gate using the PMP algorithm. And after the construction of the graph, the optimization step looks for the configuration that best fits the established keyframes and landmarks. And now Miguel is going to continue with the control, trajectory generation, and results.
Okay, thank you. For the control, to be able to control the aircraft, the simulator provides us 4 control signals to command the quadcopter: thrust and angular speeds in roll, pitch, and yaw. The simulator already has an internal PID controller that converts these signals into quadcopter motor speeds. We have adapted the control algorithm based on differential flatness designed by Mellinger et al., whose objective is to minimize the difference between the trajectory, positions, speed, and accelerations with the aircraft once. The input of this controller consists on this trajectory evaluated at the current time and the actual state of the aircraft. The output of the controller corresponds with the four control signals required that constitutes the input of the internal controller. For the trajectory generation, in order to generate optimal paths of the whole track while improving the reactiveness to changes in gate positions, we have divided this module in 2 parts, long and short-term trajectory generation. In the long-term submodule, this is in charge of generating minimum acceleration path across all the circuit. For this, we generate a path using the approximate position of each gate. As long as the aircraft flies through the circuit, these gate positions are updated with new measurements given by the perception module. With these new gate estimations, the path is recalculated, leading to an updated path. These updates are computed in real time and are constrained by the speed and acceleration limits of the aircraft. In the short-term trajectory generation, we need to generate the references for the control algorithm during the track. For this, we generate short-term trajectories that are calculated as long as the aircraft goes to the circuit. For generating these trajectories, first, we locate the drone into the long-term path, which is sampled to obtain the next drone positions within a short time horizon. These sample positions are used for calculating the minimum snap trajectories between them. This trajectory is evaluated over the time for obtaining the references that will be given to the controller. So to sum up, in the long-term trajectories, we generate minimum acceleration paths. Due to the small order of the spline polynomial and the small amount of waypoints, we can compute this path in a short time, what allows us to update the path with each new gate detection. On the other hand, the short-term trajectories are minimum snap trajectories with a higher computational cost due to the increase in the polynomial order and the higher amount of points. If you wanted to generate a minimum snap trajectory that encloses all the track, it will need a huge amount of points, which will lead to high computation times and low responsiveness to path updates. And this is why we made the division between path and trajectory, what allows us to recalculate the small sections of the trajectory as the drone advances through the circuit. And now we can see a video of our results in the simulated environment, in which we can see in white the long-term trajectory, which is updated as long as new measurements of the gates are being obtained by the system. And in green, we can see the short-term trajectory, which is plotted with an offset in the z-axis in order to ease the visualization. And so we can see how the trajectory are updated in order to pass through the gates. Then we can see the results for two different tests. One for the control and trajectory generation modules, another for the state estimation. On the left, we can see the control and trajectory generation results, in which we have obtained these results flying through all the circuit using ground truth state of the aircraft. We were able to accomplish the task in 33 seconds with a mean trajectory following error of 0.3 meters, achieving a top speed of 7.4 meters per second. And on the right image, we can see the improvements obtained when semantic SLAM optimization is applied to a visual inertial odometry algorithm such as the Beans fusion. With this optimization, we are able to reduce the mean estimation error by a 10%. So for conclude, we can see that our controller is able to reach high speeds while updating the trajectory in real time. And with the semantic SLAM algorithm, we are able to enhance the VIO post-estimation, but however, in this case, there are some parts of the circuit which there is hardly an improvement due to the high pitch angle of the aircraft, which reduce the amount of gate detections that can be seen by the camera. This issue could be improved by using a perception-aware controller that takes into account increasing this amount of detections that the camera can see. One of these perception-aware controller could be the perception-aware model predict controller that furthermore, we would decrease the trajectory error due to the abrupt changes that occurs when we update short-term trajectories. Thank you for your attention.
Perhaps we can take one question and then we can move to the panel discussion. Are there any questions? Okay, I guess then let's move to the panel discussion. So the panel we have today is all of the attended speakers who are still available. And I would like to ask, if people have questions, please put them on the chat so that we can better moderate it and we don't have multiple people talking at the same time. Okay, I mean, thanks a lot, Laura, and thanks everybody for joining. So one thing I'm going to suggest, I think, is that people, who presented, if possible, if they have their cameras on, I think that'd be great. So, when others are looking at, the attendees are looking at sort of the screen, they can see the panel. I think that when we were asking speakers if they want to be in the panel, we thought about sort of 3 things that may come up during the workshop, and maybe some of the other things that may have come up. Maybe I'll kickstart with those 3 things. I'll mention what they are and see if among the speakers, any takers to talk about any one of those 3 topics. And in the meantime, I'm going to suggest that any one of the attendees or even speakers, feel free to put your questions on chat. Make sure to put it to everyone. And then, we can see sort of what questions are coming up. And I'm just going to ask organizers, and I'll do it myself as well, maybe pick out some of the questions to discuss. Now we're quite over time. So maybe if it's okay with everybody, we can go on until the half hour. So that would be another 23 minutes. And then we can close the workshop if that's okay with everybody. So if that sounds good to the speakers, I think that the three things that we said is one of them, aerodynamic modeling or modeling of vehicles in general. How important is that? How far are we? What else should we do? Should we not do that at all? Are there any takers on that? The second one we talked about was, clearly machine learning is making a big headway. And one question is what to learn and what to model. And so if there are any questions, takers for that. And then the last piece that we asked the speakers was sim to real, whether we can really turn that into a tool where we can train vehicles far better than we can program them. So those three things that we came to mind. I'm going to ask any speakers would like to take any one of these questions after seeing the talks, and anybody else, or including the speakers, feel free to put your questions on the chat.
I can talk a little bit about aerodynamics modeling.
Yeah.
Okay. So done some research back at DLR and applied some of it at Skydio and seen a lot of data. In the context of fast flight, I just want to, I can share some tidbits of experience. Some of the things that are often neglected in classical modeling is that aerodynamics also produce torques. So typically we look at propeller models that produce a quadratic thrust depending on motor speed, and horizontal drag, which is linear in the airspeed. However, the aerodynamic forces don't typically act in the center of mass. So the aerodynamics also produces torques. And that can be a limiting factor in performance, so that the aerodynamic torques can actually induce or bring you to a state where you have input saturations, which limits the performance. The other thing is looking at a lot of flight data at high speeds. I've also looked at trying to model aerodynamics with general regression approaches, for example, with neural networks or similar. The actual structure of the forces that are acting on the dynamics is relatively simple. So we don't need very complex or deep models to model aerodynamics. But what seems to be kind of interesting is the interaction during aggressive maneuvers at high speeds. So these transients are difficult to capture. And what would be interesting is to find the good space of mapping between, like, how do we, for example, it's not just relative airspeed, it's also something encoding the maneuver that produces the aerodynamic forces and torques. And yeah, I just wanted to put it out there because this is a very good group dealing with aerodynamics and fast flight. So to kickstart the discussion. Thanks.
Yeah, yeah, I can follow up on some of the points you raised. So first, regarding the modeling of things like torque, I think that phenomenon is understood well, and I'm surprised that that's not been encoded. Like, definitely in AirSim, for instance, we do have careful analysis of torque that happens, and I would say that this it's kind of a textbook material to start with, so we could encode it. It might just be the fact that the simulation, I mean, it gets deeper and deeper, and at some point of time you have to draw a line, right? But I think you are absolutely right. Modeling torque is very important, but we do know from classical coding point of view how would that look like. Now, regarding the question of deep neural networks or regression based approaches, and I see Murli also put a question about including people from traditional robotics background. The reason why I feel neural networks is an important modeling paradigm is for the following reason. Often they are parameters of the system So for instance, if you were to just model a single drone, for instance, in case of Skydio, you do have your own drones and you model them very well. You do system ID very well on them. And once you have the physical parameters, yeah, sure, you can encode them classically. You don't really need to run neural networks or things like those. However, imagine the case that you are a researcher somewhere, and what you did was you took the DJI airframe together with some of the microcontroller from some other lab, some of the sensors, you hacked it together. And it's there, and you now want to do a lot of tests and simulation. So where do you start? Do you go and do a sys-ID again, or can you now in an easy manner fit a regression model or neural network model, right? So I think there is this trade-off where you are looking at very specific simulations in which it makes sense to do as much detailed sys-ID as possible, and then codify using classical approaches. But many times scalability means that you can get to a realistic system ID or a dynamic model of your drone and simulation ASAP. And we feel that a data-driven approach is probably more appropriate, because then you can suggest, here are the tests you run, here are the data you run, push it through this pipeline, and boom, out comes a neural network that can be plugged into this pipeline that can help. So this is just one perspective. And again, you can probably sense the machine learning bias I have in my training, but it's really trying to make that process of enabling a drone simulation as simplistically as possible without really overfitting to the form factor and to the kind of components that would be used, if that makes sense.
If I can chip in a little bit here. So I'm originally also an AI guy. So I'm not from the aerospace community originally. Now, of course, I've been working there now since 2008. But the thing is, what you want, I think, is a great goal, of course, that you have this drone and you want to be able to identify it. Yeah, you could use a deep net for it. The only thing is, you actually also want to learn it with little data. So if you need a lot of data for your deep net to learn, then yeah, that's also prohibitive for this kind of person or researcher. And the thing is, yeah, if you use a model, actually, it helps you to learn, of course, with little data. And you can, for example, identify parameters in the model, which would go quicker, I guess, than training a deep neural network from the start. So although, yeah, I mean, I sympathize with the goal and the approach, actually, because if you look at nature, and then also there, I don't know, an animal doesn't have a model of itself. It just, has its neural network, doing all the stuff it needs to do. But yeah, I do see use of a model to be able to learn with little data.
Yeah, no, absolutely. I think that's why I think just a black box approach where, there is some MLP and then you just throw data at it is not going to work. I think it needs to be thought in a very careful and modular manner so that we can augment, the knowledge that has been created over so many years using classical approaches, and then really figure out how, how could we come up with sample efficient ways of doing things? So I completely agree with that point. I mean, the only thing also we have to be cognizant about the fact is, the underlying computational fabric. So for instance, if we have too much heterogeneous modules of code that are being orchestrated, it becomes fairly complex. For instance, to implement on a drone. For instance, if you're doing any kind of model predictive control, you have to have the model. And if that model is a complex piece of simulation that are like, doing multiple things at multiple granularities, it's a fairly hard task in terms of software engineering. But if you have neural network, everything is very homogeneous computational fabric. As long as in training you have taken care and you are, addressing the issues of sample complexity, which are very important, right? So, I mean, again, this is I agree with your point. But again, pushing in the direction that, maybe that's just something we need to investigate deeper about.
And just to add a little bit at what you both have mentioned, I think the amazing opportunity of AI here is to try to get us closer to this perception action encoding. So it is in the field of neurophysiology. to some degree accepted that we encode our actions based on the perception and the other way around as well. And this homogeneity that you were talking about, Ashish, in principle, could be achieved by these models that aim to make that link. As a researcher, we may be very reasonably afraid that we will not understand this black box at the beginning. But I argue that that is just a hiccup in terms of how we're trying to implement AI at the moment, because already there is quite a lot of interest in trying to create explainable models and trying to create models where the representation is actually the output of the model. And that representation is one that in principle can be understood and manipulated and enhanced. So this to me is the big opportunity of AI. Beyond the particular requirements of the current approaches that require all these different models and the fact that there are black boxes, if we can develop models that allow us to link and encode action from perception and perception for action, I think there will be a very important step towards robotics in general. There is a call to interact virtually.
Yeah. That is very good. I feel like if any yeah, so I think that, I just saw Chris's note here. I also realized Chris joined, but I could just say, if you'd like to interact in a less formal situation after the workshop, come and join the hallway. In the virtual socializing sessions, you can go to FidLoop, and Chris just put the way to do that. And I think that, I wonder any other questions for the panel, from the panel?
I mean, one thing that always bothers me about AI, I mean, sure, I'm a proponent of AI, is the fact that we use some niceties, things like understanding, modularity, debuggability, and sometimes even safety. And to be honest, I mean, I don't have a good answer to it yet, specifically when you start considering perception in the loop as well. So that's, that's something, I mean, especially when you look at agile flight, safety of paramount importance, and it would be good to start considering them explicitly.
In the same time, these racers often crash. Yeah? So I mean, they take calculated risks. But I mean, so yeah, I must say, yeah, we shouldn't be afraid of crashing.
Yeah, but they can figure it, right? They can fix it. If they crash it maybe once, but maybe next time when they go around, they'll fix it.
Yeah. I'm not sure. I mean, they definitely, I mean, the human pilots make risk-aware decisions. Yeah? So that's definitely true. Yeah, but they do take risks, and they do crash. And that's actually what the drones are constructed for, to be able to repair them pretty quickly. And yeah, so anyway.
Yeah, no, absolutely. But also we have an issue with the sensitivities of deep neural networks. Change few pixels, so many examples there, and behavior goes completely wild. So I don't think it's an obvious route either. There are certain challenges there, and which are of different nature. So
I guess I have a question for the panel. Given the topic of the workshop, what are the remaining open challenges? Like, what are the big steps to bridging the gap to human performance?
This one is for you, Philip. No, I'm sorry.
So yeah, a quick comment on that. I mean, with this whole time optimal trajectory optimization research that we have done, we've seen that there are ways to like do these things optimally, and humans are not very good at doing the true optimum, but humans are very good at doing something very close to the true optimum that is very robust. And I think right now, one big problem in deploying these kind of extremely at the limit solutions, it's one side is state estimation and the other side is like this robustness aware controlling, uncertainty aware controlling probably, because actually when you want to execute something like this, it becomes game theory all the time, because you're always making a decision, how close do you actually want to go to the real physical drone limit? And if you touch this limit, you basically lose robustness. But the further away you stay from this limit, the slower you are. And I have no clue where this is going, but I think these are really interesting research questions that are now being crystallized out of the research that we're doing at the moment.
I totally agree. I think it's a very nice remark, because and then the game strategic concepts that we saw presented today as well. I mean, now at the moment, most people working on the drone race competitions do not take this in account at all, but human drone racers do. And so typically they don't see behind them. And so they only see it when the drone is getting in front, or they know that they're close or something. So they're definitely doing this kind of stuff. And what I would like to add is the kind of tracks that we fly. So yeah, we're coming from, I must say the first tracks in IRAS were really not simple, actually, to be honest. Very small space, thousands of all orange gates, especially if you had binocular vision. That was not easy, I can tell you. But human pilots, they fly these 3 tracks. You can even make them by yourself. You say, okay, first I fly around the pole, and then I do this, and then they make multiple rounds and improve over time. So I think also there, yeah, there's parts of human intelligence that we're really not at yet, but that we should develop.
Yeah, and to add to that, I think, you know, in air robotics, primarily we have relied on model-based approaches. So either classically or definitely, like even from machine learning point of view, that you explicitly model. When you go into the whole world of game theory, like, you know, AlphaGo, chess, or whatever, the policy they are model free, which means, you know, you are directly reasoning out the policy without explicitly constructing the underlying dynamic model. And drone racing is at this unique intersection where you need, you know, model based, because I think they have been successful, but you bring in the game theoretic aspect of it, and suddenly you are in a hybrid world. And I think it's going to be very fascinating. I think definitely this whole idea of model free, model based, working together, one trying to aspect the system aspects of drone flight, and other just the game theoretic notions. I think definitely like exciting times once we start to work together on this problem of drone racing with other competitors.
But so far, it's been more like drone qualifications and not drone racing, because there's only one drone at the track, right? When are we going to have actual drone racing?
It's called single player drone racing. So it's a special category of drone racing. But I mean, as Eric Cristoforo presented, I mean, this is coming out, but I would say this is the next stage, right? The multiplayer drone racing. We have to wait a few more years to start seeing things actually, you know, ramping up in speed. But also there are also aerodynamic effects will come into play. I mean, you can basically ask the drone now to take advantage of the aerodynamic effects. So in order to overtake the opponent, you know, because you create some vortices that can be exploded at your own advantage in the end. So all these aspects will also come back. And so how do you learn them? But to go back to the question of Theodore, what can be done? So we talked a lot about how to beat the human pilot, but still we are pretty far from human pilot performance in general, beside drone racing, right? I mean, try to do, you know, even indoor or outdoor navigation and be as fast or accurate, maneuverable as a human, considering that a human only uses a single camera, right? It doesn't have an IMU. Pressure sensor. So just the camera, 10, 20 milliseconds latency, usually poor quality. They didn't even use like, you know, the HD quality that now we have available with the new DJI headsets. And still the human brain takes 200 milliseconds. I think the thing is that the human brain actually can make use of the data in a much higher level than our algorithms. So, I mean, humans don't need state estimation, but they implicitly do state estimation. So we are actually, you know, using a kind of optical flow after all. So I think there are things to learn. Currently, we are working on I hired a psychologist, a neuroscientist in my group, and we're trying to see how human pilots reason. So we studied eye tracker to understand how they basically, you know, correlate stick commands to where they're looking at. And these are things that people have done a lot in Formula One, by the way. So we're trying to see how we can actually also derive conclusions from drone racing. So in general, I think we humans are better at making, you know, use of a little data, of a lot of data in very quick, you know, very quick times.
Okay, thanks a lot, David. I think that we're right at you know, the half hour now, and I can see, you know, I got another message from Chris. I think that, you know, they're trying to get people to attend other events. Maybe if it's okay with everybody, with this we can conclude. I thought it was a great workshop, amazing talks, and you know, some people asked, for example, what are some of the challenges. I feel like we heard from sort of across the spectrum, you know, from the kind of the machine learning to the all the way to the hardwares and the sensors and building them and a whole bunch of things in between. So it was really great. I hope that people got a chance to connect and get connected. And I look forward to continuing that and follow on conferences. And I really thank, you know, Philippe and Varun, of course, as well as Davide, but Philippe and Varun really kind of just carried all the load of this workshop. I'll put a virtual clap for the two of them, as well as all the speakers that have joined. Varun, Philippe, Davide, do you guys have any closing remarks?
I mean, you already summarized everything. It was a great workshop. Everything will be available offline, so for the future. And we are also planning to organize the same workshop at IROS, hopefully in person. If it is confirmed, the workshop was accepted, but now, you know, we have to hope for the best. So it has the same title, and we basically, you know, want to exploit the larger venue of IROS in order to have also input from other people, also from more fields. So thanks a lot, guys,
we'll
for being here. Yeah.
Thank you, everybody. Bye.
Bye. Thank you very much. Bye.
Thank you. Bye-bye.
Oh,
Bye.
can I suggest that we take at least a snapshot or something like that?
Oh, good point. Yes.
That's a good idea.
Maybe if everyone turns on their camera, we can just take a snapshot and you can put it somewhere.
Okay, that sounds very good. We can maybe Varun or Philippe can quickly snap. We can also put it on the thing.
Okay, smile. I'm snapping.
Okay.
Okay. Okay, see you guys.
Thank you. Thanks
again.
everybody. Bye.
Bye.
Thank you.
Bye.
Bye.
Thank you. Bye.